Okay guys, we come back. Mechanisms that we're going to use in order to implement the security service, we're going to use the cryptography techniques. That's why we're going to cover this one and start in maybe more details. Maybe we need 2 chapters just to go over this one. Of course, I'm not going to go more details, just to give you an idea what's going on with the encryption. We do have another class called cryptography. That class is going to cover encryption in more details, or crypto system in more details and more depth. Okay? So I'm going to do what? I'm going to just start talk about the cryptography, give you some definitions, then say, define what do you mean the cryptanalysis. Remember, every time you have someone, you have come up with some tools or mechanism in order to, let's say, encrypt something or keep something secret. There's someone on the other side, like you guys, who try to do what they can do in order to crack the system or break in the system or break the system that we have. That's what we call the cryptanalysis. Then after that, give you mainly talk about the classical cryptography. Okay, so in particular, I'm going to go over the substitution ciphers and the transposition ciphers. Again, just an examples. I'm not going to cover everything. Just hopefully by the end of the class of this chapter, you're going to be able to define the cryptography and not cryptanalysis, and you know at least some of you classical cryptography. Okay, so generally speaking, what's the crypto here? The crypto, that means anything. If you hear crypto, that means maybe I'm talking about the cryptography, cryptanalysis, or cryptology. Okay, before I go this one, let's go first, start with the cryptography. What's the definition when you hear cryptography? Cryptography, that means the way of making secret message. So in this case, when you talk about the cryptography, that means we have the message, and I'm going to hide this message somehow. If the message say hi, how are you, for example, something like this. So I'm going to do what? I'm trying to find a way in order to make this message like a secret, hide the content of the message. So you have to do what? You're going to take the plain text, generally speaking, if you have the message. This is the first one, cryptography. You have the message with the plain text, usually we call this one. Then somehow I have a magic, black box. Somehow this one is going to do what? It's going to produce a scrambled message, or the message that cannot be or hard to read. Okay, maybe you're going to see hello, hi, how are you? Maybe see A, C, D, F. Can you understand this one? Someone say, I don't know, for example. M, for example. Yeah? Somehow. Then after that, once you receive the message here, on the other side, I'm going to send the ciphertext here. I'm going to reverse the operation. So in other words, do what? I need to do whatever I did here. I'm going to reverse the steps here in order to recreate the original message from the ciphertext. So here in this case, maybe going to be hi, how are you? Or maybe being able to get the message. So again, cryptography, that is science that allow me to take care of what? Making secret message. So this is the plain text, the original message, and C, generally speaking, use the C, we call this one the ciphertext, which is the message, the scrambled message, or the secret message that is hard to read. Okay? Cryptanalysis, breaking secret message. So it looks like both are against each other. Okay? So this one makes secret message, this one try to break in. So this, generally speaking, used by the bad guys. Someone intercept the message here, get them the axe to say, for example, to the ciphertext. Then this guy tried to do what? Try to retrieve the original message. Or maybe the one other way, I'm trying to use the way of the say, remember when you perform the encryption, just speaking, use some secret ingredient or specific mechanism, or let's say magic tool, or let's say a key, which allow you in order to perform this encryption. Okay, for the bad guys here, in order cryptanalysts try to recovering the plain text from the ciphertext, or if you know the keys. If I know the keys, of course, I'm gonna that use in order to encrypt the message. That means in this case you're gonna be able to recover the original message and all the future communication of the ciphertext that are gonna be created using this key. So cryptography, secret writing, cryptanalysis, just breaking the secret message. Cryptology, that means the art of science making and breaking secret code. Okay, so this one, cryptology, both of them. Sometimes you're going to use a crypto. When you use a crypto, that means it might be a meaning cryptology or maybe cryptanalysis. Okay, and you can understand this one, the meaning from the context. Lazy sometimes say crypto. A crypto, that's me, then I'm going to see that I'm going to show you or talk about the encryption scheme. So you understand now, okay, we talk about the cryptography in this case. Then it is said in the top crypto, then after that I'm starting to show you the way how can you break in this, how could try to deduce the plain text from the ciphertext or breaking the secret. So you can understand from the context, oh, we talk about the cryptanalysis. Okay? So what's the point to have a cryptography? Why we need cryptography? Why do people think about cryptography in the first place? The most important thing that we'll start looking at, they try to have what? I'll find a way in order to have a secret or send a secret message over insecure medium. I'm communicating, for example, A and B communicating with each other. And this one I'm going to call insecure medium. That means everyone, there's many people are sitting here waiting, can read whatever I'm going to send. Yeah? It looks like now you try to talk with someone else in the same class and you left your mic on. So everyone can hear you, what's going on. Yeah. So what I'm planning to do, so I'm not going to send the plain text. I'm trying to find a way in order to hide this message. I'm sending something here. Everyone can see what I'm going to send, but they cannot understand what's going on. So that's the need of the cryptography. That's why you start people thinking about the way, how can we don't trust someone in the middle? I need to send the message in secret. Okay? So we can characterize cryptography, cryptographic systems as following. Based on the operation used for the encryption, based on the number of keys, or based on the processing of the plain text. Let's take a look one at a time. What do you mean the operation that used for the encryption? Remember, we're talking like encryption. That's what you're planning to do. You have the plain text, I'm going to use M. Then I have to do something here. I call this one encryption or in cipher. That means take the plain text, convert it to message or something hard to read. It will be C. Then after that, this is at the sender side, and this is at the receiver side. Okay? It's going to do what? It's going to take the ciphertext and try to reconstruct the original message. That's the plan. So here, the operation used for the encryption, what does that mean? We can classify different cryptography systems, the way what they are going to do inside here. What kind of operation going to be performed, the encryption and decryption? What they're going to do? The simple thing here, we call this one substitution. What does that mean here? It looks like mapping, or each element in the plain text is going to be mapped into another element. It looks one at one. So for the simplest example, let's say have A, B, C. Yeah? So you can say if the message has, the plain text has A, I'm going to map this one or substitute this one with D. If that start with, the message has B, I'm going to, let's say, substitute this one with E, for example. If C, maybe I'm going to substitute this one with A. You see, letter by letter. Of course, it's not letter by letter, maybe two letters, or maybe use in different ways. Mechanism substitution technique, but this is what do you mean by the substitution? Clear? Transposition. That means here I'm not gonna map or change the letters, but it looks like I'm gonna scramble them, mix them, change the order. So the input, for example, you have A, B, C, the output is gonna be C, B, A, something like this. So I didn't map A from 1 to B or whatever, but somehow I have a specific, let's say operation I'm gonna use in order to scramble the input here. So I'm not gonna mapping 1 to 1 or letter to letter, but in this case, they're gonna be the same letter, the same message, but it's gonna be scrambled. Okay, that's what is called the transposition. So substitution, elements, map 1 to 1, always 1 to 1, it depends on the algorithm that you have. The transposition, that means you just have rearrange or scramble the input inside. I'm not gonna map 1 to 1. It's gonna be the same. So for example, if hello, you're gonna see hello, but the letter is gonna be scrambled inside the ciphertext. The third one is combine both of them. Substitution, we're going to see by itself cannot work 100%, and the transposition not. So that's why if you mix them and you do this one in multiple stages, that means you're going to see, you're going to later the system, the first I'm going to do substitution. Then after that, the output is going to be transposition. Then after that, you do another substitution. Then after that, I don't have space, transposition. So see that we have a multiple stage, a combination for the substitution and transposition. So that's the way how can you classify different crypto or cryptographic systems based on the operation. What I'm gonna do here, substitution or let's say transposition, or we have what we call product system or product cipher. This is the name if we have a multiple stage of combination of substitution in the transposition. Okay. The other thing we can think about, how can we classify the cryptographic systems using what's called, the number of keys used. Just speaking, you're going to see some cryptographic system, we're going to use a key. Yeah, what does that mean, key? Let's give you an example here. We have a message. I'm going to use encryption. The structure is going to be the same. Plain text somehow do in cipher, then produce the ciphertext. Then after that, decrypt, then you try to reconstruct the plain text. Sometimes I'm going to use in the substitution and transposition, whatever, I'm going to use the way. For example, when you say substitution, I need to have, how can you map 1 to 1, for example? Or when you use transposition, I need to find a way in order to scramble the data. Generally speaking, you're going to build this one on, you're going to see the key, you're going to key to the cipher. In this case, that you have to have the number of rows and number of columns of the matrix. So it looks like you're going to organize the data in matrix, and the matrix must have, let's say, number of columns and number of tuples or rows. Yeah, which is the key. Anyway, either I'm going to use the same key here, one key. So whatever the key I'm going to use to perform this cipher stage, I'm going to use the exact same key. That's what you call symmetric, private, one key. That means the sender and the receiver using the same key. Asymmetric or public, okay? In this case, you are going to use different keys. Maybe you're going to key 1 and key 2 in this case. So whatever key I'm going to use in the first stage or the encryption stage is definitely going to be different than the key that you use in the decryption case stage. So we see that you have 2 different keys. Clear? The third way, in order to classify the what you call the cryptographic systems, by the way, they are independent. Okay, they are mixed. They are not mixed. Anyway, the way that how can you process the plain text? Some of them you're going to use the block cipher. What does that mean here? For the encryption scheme, you're going to see that in order to encrypt the message, you have to divide your message into blocks. And the size of each block, for example, has a specific number of bytes. So a block-wise must have a specific block size in order to start the process, or I'm going to encrypt a block at a time. And the block size depends on the encryption scheme that we're going to use, or the cryptographic system we're going to use. The other type of the processing the plain text, the stream cipher. That means the input elements continuous. So I don't need to have like block by block. I'm going to take, for example, byte by byte or bit by bit, whatever. In the data, whatever you have, I'm going to start encrypting. So I didn't need to have like or encrypt the data using the block cipher. Okay, that's just the classification or characterization of the cryptographic system in general. So it looks like I have a few terminology you need to go over them. I guess most of you are familiar with them, but I have to go over them in any case. Anyway, the first one, the cipher, which in this case, sometimes you're going to see cipher, sometimes you're going to call this one cryptographic system, which is the exact algorithm that you use in order to perform this thing. The crypto system or the encryption. Okay, plain text with the original message. Generally speaking, we use M. Okay, as abbreviation. The ciphertext with the message that's hard to read, or the message that's encrypted or coded. Okay, encryption with the algorithm. Remember that we have the message M, and this is the algorithm used in order to encrypt the message. Or in other words, I prefer to use convert from plain text to the ciphertext. Sometimes you're gonna call or say this one in cipher. Decryption. That means reverse whatever the encryption algorithm did. Yeah. So in this case, I'm gonna try to restore. In this case, if you have the message C, So the ciphertext is going to be C, and here I'm going to do decryption. I'm going to try to reverse whatever start the input is going to be the ciphertext, and the output is going to be the plaintext in this case. The key, which very important, useful information that needed in order to help me in order to decide or in order to perform encryption and decryption. Okay, and remember the key, generally speaking, use K, must be secret. If anyone knows your key, then you're done. You know everything. You can imagine your keys like, of course, not the same thing, but you can imagine this one, your password for your email. Everyone know your email address, but if they know your password, then you're screwed. Symmetric key, or the private key, or one key, is the crypto system, or the cryptographic system, or let's say if you want to say is a cipher, is use the same key to encrypt the data and the decrypt. So exact key. The sender and the receiver must have the key. The public key or the asymmetric key, in this case you use two keys. Every user is going to have two keys. The first one is going to be the public key, and the second one like pairs of key and the secret key. Okay, so everyone knows your public key, but no one knows your secret key. And it depends, by the way, I'm not going to say encryption and decryption. It depends what you try to achieve, what security serves. If you try to achieve the confidentiality, that means to send the message to someone else, you are going to use the public key for the other guy. Yeah, so he's the only one can decrypt the message, the one that has the private key. So if you do one operation, whatever, encryption or decryption, using one key, you are going to use the other key in order to reverse the operation. So we're going to see later, it depends on the security service that we try to achieve. We're going to maybe sometimes use the public key here for the sender in this place as an encryption, or maybe you're going to use the public key for the recipient, or the opposite. Okay, it depends what you're planning to do. We're going to cover this one later in more details, but just keep in your mind now, we have a symmetric key, we have an asymmetric key, so symmetric key, one key, and the same key for the sender and the receiver. And the public key, we have a pair of keys, let's say public and secret key for every single user. Okay? So, again, why we need what is called, cryptography. Okay? So, the simple thing we need in order to send a message in, let's say, insecure medium. Okay? So, Alice assumes that wants to send a message to the Bob, and this must be private over the internet. So this is Alice, this is Bob, this is Eve. Okay? So Alice wants to send a message to Bob. If you send the message in plain text, Eve is going to be able to capture and release the content of the message. Yeah? So what we're going to do in this case, what's the solution here? This is the goal. Alice and Bob wants M to remain private and unknown to Eve. So the solution of this problem, we're going to use what's called the symmetric crypto system. Or you can say private key, one key, whatever, all the name are the same, okay? So this one is what? Here we're going to use what's called pair of efficiently computable functions, E and D. E, the encryption function, D, the decryption function. Okay? In a way that this is the encryption function. When you have the message M as the input, inside the encryption here we have to have a key, K. So what's going to happen inside this one? I'm going to say encrypt using the key, the message M. Or I prefer using this. I'm going to perform the encryption for the key, for the message M using this key. That's the notation that you use in order to represent, the encryption. So the result is going to be have a C. Now we can send the C here. The decryption here with another algorithm, but we're going to use the same key. So this K and K are the same. This one must reverse the operation. So it's going to take the C, then you're going to perform the decryption using the same key, and hopefully this one is going to produce the same message. Okay? So this is the mathematical notation how to perform encryption and decryption. Yeah, by the way, this one that's me decryption, the C, and use the K here. Lower. Okay? So, what's the requirement in order this one works? The requirement that when you have if you do so this, let me write this one here. The encryption is gonna be encryption K for M, and this one was C, yeah. And here the decryption for the K for C. If you substitute C with what? With the value of C here. I'm just trying to substitute this one different. Yeah. It looks like C is equal what? Encryption of K of M. Alright? This is the C back here. And this is the decryption. This one, in order to make sure that works, this requirement, this operation is going to produce M. I just substitute the value C with how can you compute C. Then this is a requirement of the system. This one must be correctness for every single possible key K that belongs to the key space. We're going to talk about this one here. You are still being able to reverse the operation and produce M. So if you use any key in order to encrypt the message to produce C, if you try to reverse the operation using the same key, you're going to be able to retrieve the original message that you used in order to compute the C. And the security, what does that mean here? Given the value of C here, which in this case encryption of K of M, okay, without knowing the key used in order to perform this encryption, it's no way for you to find the value of M. In other words, you cannot retrieve the value of M without knowing the value of K. Okay? So just the notation that you use or components of the symmetric crypto system, the plaintext, the ciphertext, the key, or as they say, private information must be kept secret. And this is the decryption algorithm, and this is the encryption and decryption algorithm. That's what's going to happen exactly here inside the encryption and decryption. Okay? Protocol, what do you mean by protocol? So it looks like we have a protocol actually here. So when I try to describe my solution in this case, I'm going to come up with a protocol. So I need to specify the steps, what's going to happen here. What Alice is going to have, what Bob is going to have, then what Alice is going to do, what Alice is going to send once Bob receives whatever Alice sent, what's it going to do here in order to get the message or retrieve the original message. So that's what we call the protocol in general. So the protocol is composed of what? Of the compositions and the ordering of the exchange message. And also, we can have some assumption, what they know in advance before we start the process. The first thing, Alice and Bob share a common secret key. Okay? They must have Alice and Bob, they must have a copy from the key here. There. Okay? Then Alice compute the message, encryption, ciphertext, then send it C to Bob. I'm gonna say send C here. Okay? We said Bob is gonna receive C prime. So I'm gonna say, what's the C prime here? Later we're gonna have, in order this one it works, must we have what is called the channel, perfect channel. That means whatever I send, it's gonna be received by Bob. So there is nothing, there is no noise, in other words, in the channel. You know, if you study digital communication, we're gonna see that there's the noise in the message and the channel. So if the channel is perfect, that's why you have you come up with some correction codes in order to make sure that you can retrieve the original message. But in our case, we have security, we just care about the message that whatever else or C send it here, which the one gonna receive it by Bob. I'm talking about the channel. I'm not talking about the guy that tried to intercept, modify the message. That's a different story. Yes, that's okay. But the same thing, we assume that we have a perfect channel, even between the malicious guys and the recipient of the message. Because whatever the malicious guy is gonna send, that one then gonna be received by the recipient. That's why I said it's gonna be what? It's gonna be a perfect channel. Okay? Once Bob receives whatever sent here, it's going to reverse the operation and assume that it's going to be the message that's sent by Alice. Of course, right now, we didn't cover, many issues in the system. When you talk about this one, if we go back here, Alice sent the message. Eve is not going to do anything, just take a copy of the message and it's going to be received by Bob. But what if it's not Alice, the one that sent the message, someone else? We cannot discover this one somehow. Yeah? If the other one has access to the key, and then in this case we cannot protect in this case. But just go with a simple solution. Alice sent the message, encrypted, Bob received and decrypted. Okay? So what's the problem with the system here? Remember what I said. I've said something, and I was expecting one of you to say, first, how they can do that first in order to perform this operation. So what do you think? What's the problem here? Or what we need to do here before we start this protocol? Exactly, the key. Remember I said, how Alice and Bob take care of the key? How they gonna share the key? Remember, the medium that we have to use here, communication medium, is insecure. So that's another problem that we're gonna cover this one later in more details. How there's different tools, ways that it's gonna be sent. Oh, in the letter, if you send this one in the letter, that means why you need to use this algorithms. You see that? That's one thing. I mean, yeah, so in this case, why you need that system in this case? Encrypt the key with the key. Okay, so back again, how can you get that key that you use in order to encrypt that key? Exactly, one solution, we can use this one using asymmetric encryption scheme. We're gonna cover this one more details, but keep in your mind, that's what I'm planning to ask you to do here. Everything that you work with, try to see, okay, that it looks like nice, but what if? How can you do that? How can you share the key first in first place? Yeah, we are gonna go over this one more details, but this is the main reason why people start looking at the public key encryption scheme. They use this one in order to exchange the secret key used in order to perform symmetric encryption scheme. That's good thinking. Great. Okay. Let me here. I think it's here. Yeah. I did the algorithms here. Yeah. So okay. So what do we require from encryption and decryption algorithm that you use, and the computing environment in general here? So the most important thing, given C, it's hard to find M without the known key. So if you use the simple encryption decryption scheme, so anyone can decrypt the system. Yeah. For example, if your system is gonna have, for example, A, B, C, D, and just substitute A with B, B with C, C with D, D with E, and etc. So you shift only one position to the right every character. So this one is easy to decrypt, yeah? Because anyone take a look at this one, maybe try 1-2 times and say, oh, I figure out your key in this case. So we need to make sure that given the ciphertext, it's hard to find M without knowing the exact key. That's one thing. K, most of all, the key is not known to Eve. They cannot, she doesn't know this key in advance. Okay? Eve can guess the key with at most negligible, let's say, successful or success, I mean probability. What does that mean here? Assume that I'm gonna use the key, okay? And the key is, let's say, key samples with all the possible key that we have. In this case here, maybe shift one position or 2 positions. Only. This is the key I'm gonna use. So if you give me one message, if you have a letter A, I'm gonna shift it to the B. Or this shift one time to the right. Or if you have A, I'm gonna shift to the C. That means only 2 positions to the right. B is gonna be D. C is gonna be E, and etc. Something like this. So how many possible keys do we have here? Only 2, yeah? So it's easy for even gonna try to all possible key in order to crack the system. So in this case, it's not allowed. It's not. Must have one requirement for an encryption system that Alice cannot manage. Eve cannot manage in order to to guess the key. Let's say with high probability. Must spend long time in order to try to guess the key, maybe forever. Okay, so that's why we said the key must be chosen randomly from the large key space. So again, if you assume that the key is going to be 2 to the power 2, so that means, or 2 to the power 1 bits. So either going to be 0, 0, yeah, 2 to the power 2. That means we have 4 possible keys, yeah? 0, 0, 0, 1, 1, 0, 1, 1. So your key must be randomly chosen from this, what's it called? The key space. The key space, that means the all possible keys in your system that you can use them. Okay? So here looks like we have 4 keys. So it's not too large because anyone knows the size of the key. Can't tell, for example. By the way, it's gonna know the size of the key. So yeah, because you're gonna see the encryption system gonna say the size of the key, for example, 2 bits, 6 bits. Of course, not 2 or 6, but just an example, 1024 bits, and etc. So see that, and also not all the keys are valid. So 00 we don't use them. 11, for example, you don't use them. Yeah. So here now you left over, you have only possible keys. But if, for example, the size of the key, for example, 2 bits. So you have 2 to the power possible keys, you can choose them. Yeah. You have all of them zeros up to all of them ones. Yeah, we have a lot. And maybe not too much, we saw 2024 bits. 2024 bits. That's what I'd like to do here. Try to have like, that's why if you hear that some encryption scheme when you talk about later, you see that they increase the size of the key. Why? In order to make it harder for the bad guy in order to guess the key. Remember, the computation power of 10 years ago compared to today is completely different. Now we have a fastest computer. We do have what's called, you can use cloud computing. You can hire people in order to help you in order to decrypt the message, etc. And we try to guess the keys. Okay? And even your laptop maybe it's gonna be compared to the computer 10 years ago, it's gonna be has a supercomputer compared, at that time. And next month or next year. Alice and Bob successfully keep the key secret. This is the most important thing here. If they cannot do this one, this means the system is going to be collapsed. So it looks like we are going to build the secrecy, the strength of our algorithms or secret algorithm based on the secrecy of the key. If you manage to keep the key secret, then you are fine. If not, then God help you in this case. Eve cannot, for example, obtain the key in any ways. For example, social engineering tricks the user, or maybe just looking to see or watch how the Alice and Bob typing their keys using the keyboard, for example. Yeah, the same thing remind me when my kids ask them to try to log into their computer, say, look away. Why? They said you're supposed not to see our password to log in, or login information to the whatever their computers. Okay, so we're keeping blaming Eve, but if you get a chance, take a look at this slide, which contains, the side or Eve's side of the story here, where we're keeping label her as a bad guy or third party. We're gonna use this one, but she blame Alice in this case. Okay, she's honest. Yeah, she's not the bad guy. Okay. Anyway. So generally speaking, with the crypto in general, when we talk about this one, the basic assumption that we have, the system is completely known to the attacker. This may surprise some of us, okay, a few of us. They said, what do you mean that the encryption scheme is going to be available? Everyone knows what the crypto system is going to use? Yes, everyone knows what's going on. Everyone knows, for example, how your encryption or decryption scheme is going to look like and going to work in this case. Yeah, the only thing that they don't know, the key itself. The key is secret, okay? That's what is called, the Kerckhoff, principle here. One should always assume that the adversary knows, for example, the encryption, decryption algorithm, but the resistance to the cyber, whichever the encryption that you have, or cyber attack, must be based only in the secrecy of the key. And this is the reason behind this one, okay? The good thing here, secret algorithms never remain secret. Somehow they're gonna figure, if we try to say, okay, I have a secret algorithm I'm going to use in order to encrypt the message. And you keep your secret only, for example, only within our class. We come up with this special algorithm that we use in order to communicate, in order to achieve the security in our communication. Okay? No one knows about this one. But the problem is one is not going to never remain secret. Any one of you get mad for the other, or maybe get mad at me, is going to release this one, put this one on the Facebook, or say send in the Twitter, say, or WikiLeaks, or whatever, Wikipedia said, okay, this is a secret algorithm used by whatever instructor of this class. They're going to know what's going on. Okay? If you have an employee working in the organization, you kick him out, this guy is going to disclose whatever information that you have of the secret. The other thing here, the experience mentioned that, or said that, the secret algorithm tend to be weak when exposed. Because you build algorithm, secret algorithm, you test it only within your organization, or we test it only within the class. But Definitely there's a flaws in this algorithm we are not aware of, yeah? So if we keep using this one and we thought it's secret and the people knows that it's not secret and they managed to crack the system, so it's going to be embarrassing to you, okay? And it's better to find the weakness beforehand. And we're going to see that when you talk about the encryption schemes, for example, public encryption schemes of the new symmetric encryption scheme, you see that they are not secret. They tell people, they said, please, we need to have a specific algorithm, secret algorithm, secure algorithm, new one, or cryptanalysis, crypto system. And this one requires the key size, the block size, for example, and must achieve the following goal. And give the security researcher like a chance in order to come up with their idea, and they compete against each other. Then after that, they said, we have the short list, maybe have 1, 2, 3 candidate algorithms. They're gonna publish a show that the whole people, or they say people with security researcher, they said, now your chance, please try to crack them. Please try to find any flaws in the system. You see, they're gonna be tested by the specialist. Then after that, they're gonna say, we found out, for example, algorithm 1 is the most secure one, so we are gonna adopt this one. This is gonna be the official, let's say, secure algorithm that we're gonna use in the future. Okay? So what's the Eve goal? When they say Eve, this means what's the bad guy's goal? What they try to do here? They try to learn or break in your system. They try to figure out if they capture the ciphertext. They try to figure out what's the plain text. This is one goal. There's another goal. They try to do what? Try to get the key that's used to perform the encryption. So it looks like this one good. Okay, we hope if we can get this one. If we get the key, that's the better, or the most, say, goal that the bad guys try to achieve. Okay? So generally speaking, what we want from Eve. Eve wants to learn something about the information, and we try to hide. We don't want from her to know the key itself. This is the most important thing. We try to protect our key, the use in order to perform the encryption or decryption. Okay? We are not willing, or we don't want to allow her to find the ciphertext or the plain text associated with the ciphertext text, determine any character of the plain text. So try to figure out, make sure that even they cannot tell character, or you can say, for example, if you have a ciphertext, and you can tell, okay, it looks like this is the encryption of the letter A, or this is the encryption of the letter B. Because, I mean, these small things, if add up, allows her is going to be to decipher the whole system, or to get the plain text. So what kind of information we expect the Eve have? By the way, when I say Eve, this means any bad guy, okay? Generally speaking, we're going to use Eve and Oscar in this class. We assume that she doesn't have information about the crypto system except the following. What kind of type of encryption scheme that you use? For example, AES or DS or whatever, yeah? How the encryption and decryption methods works. At the same time, the ciphertext. We expect that she has access to the ciphertext. That's what the blind have. That's what our assumption is. But generally speaking, the bad guys always knows more than what we expect. The first thing that we thought that he might has access to, she might have what is called, the message distribution. For example, you speak English. You're writing your message in English, and when you type your message, you're speaking when the first letter or the first paragraph or statement say, hello guys, or hi guys, something like this. Okay, oh, there. So that's one information that knowledge can help her in order to try to crack or break down the ciphertext. She might have obtained, for example, several other ciphertexts. We don't assume that she just started now. Maybe she monitored the system for a long time. 1 month or 2 weeks ago, and etc. Yeah, so she could actually have access to many ciphertexts. That's why when you work with an encryption scheme, we encourage the people, don't use the same key for a long time. Try to modify the key. Okay, we're gonna see this one later when we talk about the key distribution and session key and etc. She might have, for example, learned decryption of earlier ciphertext. Because again, she monitors the system. We're gonna see how she knows that. She might have, for example, has from C1 up to CN. Or let's say 100 ciphertext. She might, after that, she knows that the plain text associated with this ciphertext is M1 later. Okay, she might be choosing, the earliest message or the ciphertext herself. This is when we're gonna take a look here. So might be, by the way, we didn't say anything about the Eve, whether it's gonna be legitimate user or not. It might be someone here working with the IIT, and this guy tried to crack the system, or tried to figure out the other people or other employees when you try to communicate with each other. Okay, so it looks like we need to consider several attack scenarios that Eve has extra piece of information, and we need to define different scenarios, attack scenarios. Then after that, when you build your encryption scheme, you try to make sure that my encryption scheme can withstand this attack scenarios and etc. Because again, she might have even choose the early message or ciphertext herself. We're gonna see how she can do that. So this is a different attack scenarios, okay? The first one, or the simple one, the ciphertext, or the ciphertext-only attack. What does that mean? That means that Eve has only access to the ciphertext they try to decrypt. Only, nothing else. Of course, you know what the decryption scheme used here, or algorithm, and the ciphertext. Now she tried to figure out, to find a way, how can we find out, or reverse the operation in order to get the plain text. This is the simple thing with the ciphertext attack. Okay? The second type of the scenario, that means she might have knowledge. It might have to say, as I mentioned here, choosing the earlier message or the ciphertext by herself. So let's see how it works here. How can we inform that? The second scenario, we'll call this one non-plain text attack. What does that mean here? She knows, for example, what? Of course, the ciphertext that you wanted to crack, plus something else. What else? It's going to have what is called a sequence of what? The plain text ciphertext pairs. Okay? And she tried to recover M from C. So it looks like I'm monitoring the system, and they do have access to the following. Assume that you have M1, message 1, and the ciphertext, the corresponding ciphertext with message 1. M2 and the corresponding ciphertext of the message 2. Assume you have, how you said, to R, okay, and CR, okay? Then you give me, for example, CX or C. Make sure that C is not the one that you already have the corresponding plain text. Then you, based on this knowledge or this information, this plus C, you need to figure out the plain text associated with this message. Okay? So that's the knowledge. The first one, you have only the ciphertext that you need to crack or break it down, or that you need to decode or decipher. The second scenario is that she has more information. There's a sequence of the plain text ciphertext pairs, M1, C1, up to whatever, how many, it depends, plus the message that, or the ciphertext that you wanted to decode. This is the second scenario, known plain text attack. Okay? You need to understand the difference between them. Then, someone may be wondering, said, okay, you said known plain text attack. How come Eve can get access to this pair, let's say, sequence of the plain text ciphertext pairs? Let's take a look here. How? Alice maybe used the same key to encrypt several messages for a long time. Okay? At the same time, Eve later learns, for example, whatever, or can guess whatever the corresponding plain text. I know that you work with the key for a long time. It's going to be the checker going to manage to have, or can build what's called the pattern. You're going to tell, for example, oh, it looks like this guy is, for example, you communicate in the class, okay? And send you something, then you apply something, okay? Every morning or beginning of the class or before the due date, etc. So you can, by monitoring the system for a long time, if these guys communicate using the same key, the chance in order to guess the information, decipher the ciphertext is going to be high. Okay? There's another way maybe you can learn the plain text. So it might be, for example, publicly revealed. Just speaking, maybe you have a sealed bit in auctions. For example, A, B, C communicate, and security, this is the highest bit, encrypted, I cannot tell. Then after the auction is done or over, now they're going to release the highest bit was, for example, $1,000. So I can say, okay, this is the ciphertext, and this is the plain text associated with ciphertext. That's one thing. Or maybe it's easier to guess, the plain text. I know that, for example, of course, it depends on the social engineering. We'll try to cover this one later if we got a chance. a monitor, and they know that your behavior. And when you communicate or send the message, maybe the first thing you say, they're all something like this, or hi guys, whatever. This is the header of the message that, or the email that we got. So I can't tell by the monitoring, the communication in the game. It looks like, what if this one's they're all? I'm trying to perform this one. Guess this is going to be the corresponding plain text with the ciphertext. Then, of course, the more information that I got, the higher the chance that I'm going to break the system. Okay, we're going to see later. We have an example, one activity. Maybe you're going to perform this one if we finish the theoretical part today, or maybe next lecture. This is like fun. I give you ciphertext. I give you like cryptanalysis sheet. Then I will ask you to try to guess. The ciphertext. The plain text. And you're gonna have fun. I guess maybe you need 15 to 1 hour maximum. Then you're gonna be able to get the information that you're looking for. Recover the plain text. The other thing, maybe even gonna have what? Managed to compromise pop computers. I found all the decryption, or let's say the plain text or decrypted version of the ciphertext stored there. So we have different ways. Okay. So we said we have different. Attack scenarios. The first one, the Ciphertext-only attack, which Eve knows only the plain text. The ciphertext that you want to decode. The second scenario is that non-plain text attack. That means in this case, Eve knows 2 pieces of information. The first one, the ciphertext to be decoded plus a sequence, to say, of the plain text ciphertext pairs. Okay. The third type of the attack here. Now, I'm still talking about the extra piece of information, which is the sequence of plain text ciphertext pairs. For the non-plain text attack, it's going to be known in advance. Okay. For the chosen plain text attack with another scenario here, this is what say here. I'm going to play around. I'm going to let Eve choose either the plain text part or the ciphertext part from these set of sequence of plain text ciphertext pairs. So the chosen plain text attack, the same thing. I need to have. Actually, I gotta know what is called. The ciphertext to be decoded plus. Now, Eve choose the plain text. So you have a chance as the attacker to choose M1 up to MR. Then you are going to send this information to the system, and the system is going to encrypt them, give you the C1 up to CR. So now you have more control about the content of the plain text part of the sequence of plain text ciphertext pairs. Okay. Of course, you're gonna perform this operation before you get the ciphertext. Okay. This one thing. That's a chosen plain text attack. The chosen ciphertext attack is gonna be the same definition that we use the chosen plain text attack, but in this case, Eve is gonna choose the ciphertext. Okay. Before getting C. Someone says, how can you choose the ciphertext? We're gonna see later. It depends on whatever the encryption scheme that you want to perform. For example, your encryption scheme is going to produce 1024 bits. That's the length of the ciphertext. So it's easy to come with 1024 bits symbol, yeah? For example, all of them are going to be ones. Then after that, all of them change only 1 bit to see how the system may act in this case. That's what you're planning to do. Then you choose 2 bits. Then after that, send to the system to decrypt to see whether they're going to change anything or not. Okay? So the chosen plain text attack, or chosen ciphertext attack is going to be the same. The only thing that the Eve is going to have a chance in order to choose either the plain text or the ciphertext. If you choose the plain text, send it to let's say the server is going to encrypt the message or decrypt the message in the case of the choosing the ciphertext. Clear, guys? The other scenario, which is going to be a stronger attack in this case, I'm going to mix chosen plain text, chosen ciphertext attack. I'm going to mix both of them, this information. So since we have, for example, M1 up to MR, and you have C1 up to CR, this is the original information that we have. So I'm going to say, for example, I can choose to say, let me have different color, M1 up to MR divided by 2. This is going to be chosen as the plain text. Send it to the system of the server, and they're going to receive from C1 up to CR divided by 2. Then after that, I'm going to choose this, say in this case, the ciphertext with R divided by 2 plus 1 up to CR. Then send it to the system, and they're going to give me, for example, the corresponding plain text. So you can't choose whatever the path. Some is going to be ciphertext, and some, corresponding, the plaintext. Okay, that's what we're trying to do. If any encryption scheme, anyone come up with encryption, or let's say protocol, they said my protocol is secure. This is what kind of attacks that you try to, to perform against this kind of system in order to prove whether the system is secure or not. Of course, when you build the system here, a security system, you're going to say, for example, my system, for example, withstand choose a plaintext attack, or choose a CyberText attack, or maybe mix a choose and plaintext attack. That's one property that your system is going to achieve. Okay? What else we can do here? We can do this one. Instead, we have, give me a second here. So one question, by the way, before jump to the adaptive here. The question here, why Alice, or let's say Bob, is going to encrypt to decrypt the message from you. Remember we said in the chosen plaintext or the chosen ciphertext, the Eve is going to choose, for example, either the message M1 to MR, or it's going to choose, let's say, CyberText C1 CR, then send them to the Alice or Bob or the server, either going to perform encryption or decryption. So the question, why are they going to involve this situation? Where are they going to help them? Again, we didn't say anything about that Eve is unknown to the Alice or Bob. It might be a legitimate user, and this user maybe is going to encrypt to decrypt the message in the system, but only your messages, not someone else. Yeah? Or maybe Alice is going to be the server, which allow us in order to send the message to the server is going to encrypt it to me. Or send the message to the server, it's going to decrypt it to me. Okay? Of course, it's going to tell, for example, whether they're allowed in order to perform this operation or not. That we call the access control or authenticate the user is different story. Otherwise, someone has said, if the system is not secure enough, so maybe I'm going to send the C message that I want to decrypt to the system, and hopefully the system is going to decrypt it to me, for me. No, in this case, not. When you send something to the server must authenticate you whether you are allowed to perform this operation or not. Who's originated this message? Me. That's my message. Then I can do it for you. Okay? So again, maybe Eve authorized to generate a message, then they encrypt it and send it to the Bob, but is not authorized to read the other people's message. So still legitimate user can perform this operation within the system. Okay? Or maybe, as you mentioned, one of either Alice or Bob is going to be a server that allows you to perform the operation on behalf of the other users. Or Eve maybe gain access to the Alice computer. Alice is not staying for a long time with her computer and left her computer on, then perhaps maybe you can, Eve is going to, for example, get access to the Alice computer and try to retrieve the information, or maybe send the message encryption and decryption on behalf of, using the Alice computer. Someone has said, no, we don't do this one. Actually, 2 years ago in the IT, it happens many times. My office, when it came to the IT, used to be in the low level, in the same level of the labs. Within the labs, there is a room hidden, used to be my office. I know that when I came there, the first time they said, that's your office. Anyway, so when I usually I leave my office late because of the traffic, then I noticed that some computers out there in the lab are on. It's working and is not locked. You're still being able to see some people's emails are open. They're leaving their email computer active and the email is on. It's available. So you can, the browser is opening the email, so you can do whatever on her computer. Anyway, so that's how can we, the Alice or Bob is going to cooperate in this operation. The other thing here, of course, in the real application system, we try to test that. We are going to use Oracle. We try to generate, because we know the encryption scheme, we know the length of the key, so we can tell, for example, what's the format and the message is going to be here. For example, either bits or ASCII or whatever. Okay? The other type of, version of the scenarios that they cover here for the attacks, we call this one the adaptive. Choose and plaintext attack. It's similar to the choose and plaintext attack, but here in this case it's different. I'm going to say adaptive. That means I'm not going to send you, for example, or receive or choose the message M1 up to MR at once or one time. No, I'm going to do this one at a time. So let's say choose and plaintext attack. I'm still being able to choose from M1 up to MR, yeah? But I will do this one at a time. I create a message, for example, transfer $1,000 to user, then send it to the server. Then I'm going to get C1. Then by monitor M1 and C1, I'm going to say, okay, what if I'm going to add white space, or maybe I insert a new entry, or change from $1,000 to $2,000, for example, and see the pattern, what's going to happen to the message of the encryption here, message, or the ciphertext message that they got after I perform this. So when you send M1, create M1, receive M2, C1. When you try to send M2, M2 is dependent on the M1 and C1, because I'm going to take a look at the value, monitor the behavior, the pattern, then create M2, then send it in order to receive C2. So in order to send M3, it depends on what? M1 and C1, and also it depends on M2 and C2. This is one of the strongest attacks here. Okay, because now if being able to manage to do that, that means you have full control. You choose messages one at a plain text, one at a time. Every time you can send it to the server, get the corresponding ciphertext. Then after that, based on the pattern, you see what if I change or add space. Sometimes add some space only to the message and see what the action, what's going to happen to the system. Of course, we're going to build our system in a way you're going to see today that we try to hide the relation between the plain text and ciphertext. In other words, it's not easy for you, to even add one space. Maybe you're going to have the ciphertext is going to be changed in many places, not in one place. Because remember, 1020 bits as the input, I'm going to get, for example, 1024 bits or 2048 bits as the output. If I change one bit here, I will see what's going to happen in the rest. You see that? Remember, and it's not only one message, it's a number of messages. Try to study, analyze the ciphertext and plain text. Anyway, that's what we call the adaptive choosing plain text attack. For the adaptive choosing ciphertext attack, that'll be the same thing, but I'm going to choose, I'm not me, it's Eve, of course, is going to choose the ciphertext C1, then send it to the server, decrypt it. Once you get the message M1, I'm going to see, okay, what if I change 1 or 2 bits? And of course, you have to organize this operation in order to have it's not randomly to change the bits, okay? I know the locations that I change, then I will see what's going to happen to the plain text, how many bits is going to be changed if I change 1 bit or flip 1 bit from 0 to 1. This is the adaptive choosing ciphertext attack, and mixed attack is going to be the same thing that we talk about the mixed choosing plain text choosing ciphertext attack. That means you choose some plain text or some ciphertext, but one at a time, okay? Okay, those are the scenarios that we have, attack scenario in general, based on the information that what Eve can have, okay? We define, generally speaking, only a relatively weak algorithm failed to withstand ciphertext-only attack. In other words, if we found any system that cannot withstand the ciphertext-only attack, remember that means Eve has only access, or let's say the ciphertext to be decoded, and she's going to try to recover M. If your system fails, cannot withstand this kind of attack, then don't use it, okay? That's what we call weak algorithms. Actually, too weak. We're going to take a look at some of them today. Okay, so just speaking, that the encryption algorithm is going to design at least to withstand the known plaintext attack. That means in this case, remember, just to remind you, the definition is going to have, Eve is going to know the ciphertext to be decoded, plus, the sequence plaintext, ciphertext, pairs. Okay? You know that. So the question here, how can you compute the cost of a breaking ciphertext? Or in other words, how can you define what's called, whether my encryption scheme is strong or not, or whether my encryption scheme is computationally secure? We can define this one as following. The cost that for breaking whatever the ciphertext is going to exceed the value of information. For example, you're going to spend $1,000 in order to crack or decrypt or decipher ciphertext. So at the end, maybe it's going to give you as maybe you're going to give me a word $100 or give you a gain of $100. So you spend a lot of money in order to get nothing. You're going to spend your money for nothing. That's what we call in this case the encryption is computationally secure. Or, this is the best definition here. The time that you need in order to break the cipher or the ciphertext is going to exceed the useful lifetime of the information. Assume now you're taking this course with me, okay? And maybe I'm going to encrypt, let's say, the midterm exam, okay? And you need, for example, 3 months in order to decrypt or manage to get, I mean, the midterm exam for this class for this semester, yeah, and the plain text. If you spend 3 months, and once you manage to successfully decrypt the data, it's not going to be useful anymore. Yeah, the same thing, the final exam. Maybe spend 10 years to decrypt that. 10 years, good luck. After the end of the semester, I'm going to publish the final exam. Or during the exam time, everyone is going to know this information. No, I mean, I'm just trying to find out, just to define the computational security. Yes, if you just want to get the free credit, maybe get A, okay? But if you have this, for example, this is CyberText, okay? Then you're gonna spend, for example, let's say, assume that 10 years, or let's say 1 month, in order to decrypt this information. And this message is gonna, or the ciphertext contains sensitive information that you needed or can be valid only for next week. So you spend long time for nothing. Yeah. In other words, I'm gonna say the encryption scheme that used in this in order to encrypt the message, the plain text in this case, is computationally secure. Yeah. Because even if you manage to decrypt the message, you're not gonna gain anything. I mean, whatever you're gonna gain is gonna be is not useful. Yeah. Or it's gonna exceed the value of the information that you get. Okay. Generally speaking, it's hard to come up with the time. For example, you're gonna say 1 month or 2 months in order to decrypt the system or to break the system. That's why we can estimate the time, okay, or the cost of what is called the brute force attack or exhaustive key search. What does that mean here? The easiest thing, or the straightforward attack in this case, I'm gonna say what? I'm gonna try every possible key. Remember, the message, when you encrypt the message, you have the message, you have the encryption, you're gonna use somehow key, then you're gonna produce encryption of the message, yeah, equals C. Then I'm here on this side, I have C. What I'm trying to do here, I need to take C, yeah, as input, you say decrypt, okay, for the C in order to figure out the M. How can you perform this operation? I will try every possible key that we use in the system. If you have the key, for example, the size of the key, for simplicity, okay, only 2 bits, that means you have only how many keys? 0, 0, 0, 1, 1, 0, 1, 1. It's you have 4 keys that you have to try at most in order to figure out the corresponding message. Okay, that's what we call the brute force attack or the exhaustive attack. So we can estimate the time, the cost of that, how long it takes from you in order to try every single possible key. Okay, this is not enough, by the way. It's not that all, because always when you work with encryption, definitely there is a shortcut, which is the one that we try to work on right now. So anyway, so exhaustive, or to say brute force key search, means that the bad guy tried every possible key. Okay, and we assume that she is able in order to distinguish or figure out whether the message is the plain text, the right message or not. Because sometimes you're going to see that different keys maybe going to produce different plain text. So assume that the bad guy being able in order to distinguish which one is the right one. Okay, of course it depends on, it's not the first plain text that they got. I know who's communicating with what. I'm expected that they're going to talk about, let's say, the final exam, or maybe they try to send sensitive information, or maybe talking about me. Okay, what's it? So in order to prevent what's called the exhaustive or brute force attack, a crypto system must have a large key space. That's why we're going to keep say the large key space. Assume that we have the K space. Let's say 2 to the power, let's say 1. That means 2 bits, yeah? 0, 0, 0, 1, 1, 0, 1, 1. Yeah? Instead we have 2 to the power 1. Maybe I'm going to say 2 to the power 1024. Or maybe 2 to the power 2048. So see how many possible key that you can perform. Make it harder for the bad guy in order to try every possible key. Okay, that's what you call the key space, the set of all possible keys that can be used in order to perform the encryption or decryption. I will try to make it too many for that. Again, instead we have to say 0, 0, 0, 1, 1, 0, 1, 1. I'm gonna have 0, let's say 2048 zeros up to 2048 ones, and you see how many you have 2 to the power something. If you tried all of them, it's hard to perform this one. You're gonna spend a long time, maybe the whatever. I mean, end of the universe, maybe lifetime with the universe, try to crack the system and make it worse. Duplicate I think the 94 guess, something like this, or 69, 96. Yeah, so make it harder. That's why if we hear the encryption scheme, we use the same encryption scheme, but we're going to increase the key size because now the computation power is allowed to the bad guys in order to collaborate together using cloud computing, using multiple users at the same time, divide the key space and try all the possible key. So that's why we increase what? We keep in the same encryption scheme, but we increase the key size in order to make it harder for the bad guy in order to iterate or try every possible key. But someone said, do you think that the large key space is sufficient? If you increase the size of key and said it's okay? No, it's not. Because definitely there's a shortcut attacks. We try to take a look at some of them during this class. So in other words, there's some, I mean, you see that some cryptanalysis technique, we can use them in order to, instead, I'm not going to go, of course, the solution in order to crack any system to try every possible search key. But you cannot do it right now. Why? Maybe you are son or whatever, billion of years, it depends on the size key, that require you to check every possible key. Someone has said, maybe I'm lucky, whatever the key I'm going to choose is going to be the right one. Never happened. If you're lucky, I don't know, but it's never happened. Okay? Anyway, the shortcut, that means instead to try to pass every possible search key, or let's say the key the user will perform the encryption, I'm trying to find a way in order to reduce this one. There is some technique you're going to see that maybe you can divide or reduce the search effort by, let's say, the key size divided by 2. Makes you have the time that you need to find all possible key, and etc. And again, in the cryptography, we cannot prove, or never prove that there is no shortcut attack exists for any encryption scheme. Okay, so back to just summarize what the attacks can do. The goal of the attack is the first thing you're looking for, try to discover the plaintext. Okay, which is good. If we got a chance or managed to discover the key, wow, that's what I'm looking for, that's perfect. And what I'm gonna do here, because if you discover the plaintext, I know only the plaintext corresponding to this ciphertext. But if I know the key that you use to perform the encryption, and we know most of the people are lazy, we're gonna use the same key over and over and over. For some of them use the same key for years. So in this case, I'm being able to manage all or decrypt all the exchange message. Also the previous one and the new one and the current one. Okay, if they use the same key. Okay, we assume that attacker knows the ciphertext, of course, the algorithm used in order to encrypt or decrypt of the crypto system algorithm. Plus, they have like a sequence of the plaintext ciphertext pairs. Okay, which use the same key, of course. It's used different keys. It's not gonna keys. That means it's gonna be it's not helpful. Yeah, because I cannot use them. The main attacks methods. The first one, the what's it called? I mean the brute force attack. We try every possible key, which is gonna be take long time to perform that. Or try to use some cryptanalysis technique, which try to find a shortcut. Okay, in order to discover the plaintext or the key. Okay, and again, we assume that the attacker can manage or recognize the correct plaintext. So right now we're going to take a look at some examples with the crypto system. So we're going to take a look at the classical or the historical one. All of them are going to use what is called the symmetric encryption scheme. That means we're going to use the same key for the encryption. It's going to be the same key for the decryption. Okay, so the first example you are familiar with Caesar scheme or crypto system. Okay, so in this case we call this one the simple substitution. So what I'm planning to do in this case here, in this case, substitution cipher means is, by the way, it's the most common form of the ciphers. Okay, and the way that works is by replacing each letter. You have the plaintext, whatever the plaintext they say, let's say hi, okay? For every single character, or letter of the plaintext, it's gonna be like with another letter. So if you found H, replace this one with X. If you found I, replace with Z, and continue for every single letter. By the way, for simplicity, we assume that we have only work with the English language, so we have 26 letters. Okay. Some schemes you can use, for example, punctuation, special character. They're using what you call, the numbers, etc. We can include this one. But for simplicity, let's just focus on the English letter. That means we do have 26 letters. We need to find a mapping one-to-one. Okay? This is the simple case. So here assume that we have this the plain text. Sometimes we use the plain text, for example, I'm going to use for and use X in order to separate, one word with the other. Here I didn't use any separation, okay? So just put them in one plain text. Just for simplicity, for just illustration purpose, we're going to use the plain text, write the plain text in the lowercase and the ciphertext in the uppercase. Just, for illustration purpose, okay? So here, this is a plain text. The way that we use the substitution, simple substitution, I'm going to perform the following. I have list the 26 letters from A to Z. This is a plain text. And this is the ciphertext. Here I'm going to use what is called the shift, or the Caesar shift, or shift cipher, or the Caesar encryption scheme, or crypto system. In this case, you have to shift every single letter to the right by 3 letters. So if you have A, I'm going to shift 1, 2, 3. So A is going to be D, B is going to be E, C is going to be F, and etc. You see, so Z is going to be 3 letters, it's going to be A, B, C, and etc. Okay? So if once you find whatever the plain text here, try just to map it to the corresponding ciphertext. This is how can you perform encryption. In order to perform decryption, you have to go to the reverse side. You start with the plain text and try to map it to the corresponding ciphertext. So this I'm going to say encryption, and the reverse side or the other direction of the decryption. So take a look at the first letter, F. I check F here, it's going to be I. And the second one, O, I check O, the corresponding there is going to be R. Okay? When you try to decrypt this one, that means I have this is the ciphertext. Now I need to decrypt. You have to have the share of this table. Oh, the sender and the receiver, that means we're going to use the simple substitution. That means we're going to shift, in this case, the Caesar one. By the way, we have different types, okay? But here I'm just focusing on what you call, as example, the Caesar shift, where we shift the letter 3 digits or 3 positions to the right. Sometimes you can do this one to the left, yeah? You can do whatever. So here, I start with the ciphertext I. What's the I here? And you need just to go to the other direction. So I start with the ciphertext, and the corresponding value is going to be F, and the R here, and they're going to be corresponding value is going to be O, and X, to say, just to give you this example, it's going to be A, if O, X, yeah, it's U, and that's it, okay? So you manage to decrypt the message. We call this one the place remains the same throughout the message. That means if the simple thing, every letter is going to be shifted to the right by 3. It doesn't mean that, no, then after that you change your right. Maybe another letter is going to be shifted by 6, and etc. No, all of them are going to have the same structure, the same, let's say, mapping technique, or the shift to the right, for example, by 3 or by 6, etc. This cipher is called monoalphabetic substitution. That means we're going to use a fixed replacement structure. In this case, in our example here, whenever you find A, mapping to the D. Always. Okay? Regardless of position. B must be mapping to the E, and etc. Okay? That's the simple one. Okay? This is the, how can we, this is just example again for the ciphertext, different example. If you have the ciphertext, then you need to figure out how can we perform the plain text. I like this one. If you have a V, this is the ciphertext here, it's going to be stay, it's like S, and the W is going to be T, and etc. So stay home and stay safe, save lives. Okay? This is an example. In the example, we can give you like something like this. I'm going to say, for example, you're using Caesar cipher. This is the message, or this is the ciphertext. What's the corresponding plain text? So just I want from you to know what kind of algorithm we're going to use, how can you perform encryption, and how can you perform decryption. Okay? This is the simple way how to perform that. And this is as example for the substitution cipher. The most famous one comes after what's it called, the Caesar ciphers. Okay, shift by 3 always. But we can do whatever shift in general case. So let's have some mathematical notation. How can we maybe figure out a better way? Instead we have a table, go back and forth with the table. Maybe have another way in order to perform this operation. Assume that M is going to be the plaintext. Well, in this case, so M is going to be any letter from A to Z. Yeah. K is going to be the key space, all the possible keys that we have. And you see the possible keys is going to be, for example, this one, K is going to be from 0 up to 25. Because either we have 26 keys, yeah? Either shift 0 position, that means the plain text is going to be the ciphertext, don't use it. Or shift 1 position to 1 letter to the right, shift to 2 letters to the right, and etc. So you have 26 possible key you can come up with. You can choose. So that's, we use the K, small k is going to be between 0 and 25. Then the encryption and the decryption algorithm, we're going to use this one to say use modules in order to how to mathematically describe the encryption and decryption. Before I perform this, I'm going to represent the data, okay? Or let's say transform the letters into numbers. So I say I can assume that if you have A, it's going to be 0. If you have B, it's going to be represented by 1. Z is going to be represented by 25. Just in order to simplify the process, we try to find out a way in order to describe the encryption decryption mathematically. So the encryption, the key, by the way, is going to be an integer between 0 and 25. That's what we did. Then the encryption is going to be, by the way, you can use the table or you can use this mathematical, notation here. The encryption, you have the message, okay? For any message M, I see M is going to belongs to the M. So any letter, maybe the message, for example, I say ABC. This is our message. So take 1 letter at a time because we perform this operation letter based. Yeah, right. Take the letter. Find the how can we transform this number into how can we transform this letter into numbers? A is going to be corresponding to 0, B corresponding to 1, and C corresponding to the 2. So the encryption is say of 1 or 0 of A based on the key. So here it depends on the key. What do you want to do? Shift by 0, shift by 1, shift by 2, by 3, whatever. Let's say shift by 3. Or just for simplicity, okay? So in this case, encryption is going to equal to the message with A, 0, plus the key that you use, plus 3, and you need to compute this one mod 25. Once you have the value, you know what's, of course, we have like the mapping for every single letter into numbers, and I know this one 0 plus 3 is going to be 3, so I have CD, it will be 3, so in this case the result is going to be D. In order to decrypt the message, you need to do what? Use this formula, okay? So you have in whatever the ciphertext, in this case it's going to be D, yeah? And I know D is going to be the binary representation, or to say the when you map this one into numbers, it's going to be 3, okay? In order to decrypt this one, you have to use the same key. So decrypted key equal 3 for the message equal D is equal the following. I'm going to have 26 plus what's the value of C? In this case, it will be 3 because I'm going to do letter-wise, letter by letter, decryption and encryption, minus the letter. Did I make the mistake here? Yeah, minus the letter 3 mod 26. So this one will be 0 here, yeah? Which in this case, if you go back to the letter, the mapping for each letter to the numbers, you see this one is going to be A. So this one way in order to perform this operation, or maybe you're going to use the tables. Either is fine, okay? So this is a simple thing. Let's take a look to not simple substitution in this case. So not to the by 3, maybe it's going to be by any number. So just generalize this process here. So here we're going to use the k equals 7, and in order to build the table, this means it's going to be 1, 2, 3, 4, 5, 6, 7. So A is going to be H, B is going to be I answer. Okay? This is the plain text, and this is the ciphertext. Encryption, this is the way, or this direction in order to perform the decryption. So far so good, I guess. So how can you cryptanalyze? How can you try to discover the plain text given the ciphertext? Of course, you need to know what? you need to know what encryption scheme you use. I'm going to say simple substitution. Shift, let's say, to the right by 0 up to 25. Okay? I give you the ciphertext, but I'm not going to give you the key. So now you need to find out to try to find or figure out to see all the possible keys here. So if you give you this ciphertext, okay, then you need to find out how can we decrypt the message. So just speaking this one, basically you can check. It's gonna be, I think you are terminated in this case. Yeah, I guess. Yeah. So this is the plain text. So the key is gonna be have what? You have 26 keys from 0 up to 25. We can eliminate 0, shift to nothing. So this means C is gonna be C, S is gonna be mapping to the S, because in this case it looks like it does make sense. It's not valid to say a phrase in English language or statement. Okay, so that means eliminate the first one. So you have 25, possible keys. Shift by 1, shift by 2, shift by 3, shift by 4. By hand, it's gonna take time. There's many available software, you can use them, or maybe you can build your own software in order to allow you to give the message, and this software is gonna try to perform or try to decrypt the message using 25 keys or 26 keys. For example, you can say K, key 0, this is the plain text that you come up with, or M. 1, this is the plain text. 2, this is the plain text. And etc. You take a look at the 26 possible plain text, and you can tell hopefully the one that makes sense to you. You say, this is, it looks like this is the plain text that we're looking for. Okay? So that's the way to cryptanalysis, again, try to discover the key of the ciphertext, of the plain text, sorry, of the given ciphertext. This is the way how to, the simple thing, try to iterate over every possible key. There is another type of the substitution, okay? I'm keeping saying simple substitution, okay? This one I'm gonna use different way. I'm gonna use permute, the alphabet. What does that mean? Right now, if we say, we do have like fixed, substitution. From my data, or the whole data, or all the letters, it's gonna be shift by 3 to the right. All of them must be shift by 3. But here it's gonna be different. I'm gonna say, I'm gonna permute what's called the alphabet. For example, the first, let's say, letter or A is gonna be mapping to the J. B is gonna be mapping to the X. C is gonna map to the C. So it's not fixed. The pattern is not fixed for the whole keys or the whole alphabet that you have. So again, we are going to substitute a letter, for example, with a J in this case, if you have 8 with J. Then we have a cost of, that means I cannot use J again. Can I use this one again in order to map another letter in the plain text? No. In this case, if you use this one, we use the same ciphertext, or let's say you have 2 letters, A and C, both of them are going to be mapping to the J. So how could you decrypt? Remember, we need to find the way in order to allow me in order to recover the plain text. In this case, we cannot do it. Okay? So every time you have from A to Z, you can specify for A, I'm gonna map it to the J. Then you cross the J. So out of 26 possible keys, we can map this one, either to itself or any other key. Yeah? So in this case, the 26, I'm gonna cross this one. That means for the second letter, I can map it to the rest of the keys, of the available ciphertext, or the available, let's say, alphabet. So in this case, you do have 25 possible keys you can mapping B to. So in this case, you assume that B is going to be mapping to the I. Now I is going to be crossed from the data. That means for the next letter, you're going to have 24 letters going to be, you can choose from. Okay? For the first one, you have 26 possible, let's say, combination, let's say, way in order to map this one to any valid alphabet. For the second one, you have 25, because the first one, you have to exclude 1 because you used to with the previous key. For the third one, you have 24, and etc. So it looks like, what's the number of keys, or how many possible keys in this case? It's not compared to the simple, shift cipher. Everyone's going to be shift by 3 or by 4. Here it's going to have what? For the first letter A, I need to find out 26 possible keys, or mapping to all the, either itself or to the rest of 25. So the first one, you have 26 possible keys. So it will be, as you said, simple shift, but only apply for this one. You said shift by 2, for example. Or here for the J, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first one, you shift by 8. So for the second one, you shift by what? By 1, 2, 3, 4, 5, 6, 7, by 7, and etc. This is another way to understand this one. But it's not fixed. For every single key, it has its own mapping. This is the better, I mean, it's better to say that. So the first one, you have 26 combinations in order to find the right one. For the second one, you have to try what? 25 different keys. For the third one, you have to try 24. And you continue this one until for the last one, you're going to have only try 1. So it looks like we have 26 factorial. And this one, this is the number of the keys that you end up with. How long it takes in order to decrypt this one? It's going to be too long time, okay? Lengthy time. So if you try to find all possible key combinations, in this case, it's going to be, you have to do this one for a long time. I mean, you have to try every possible combination of the keys. So the brute force attack in this case, of the key exhaustive, is not working well, okay? Because we cannot combine this one. So does that mean this encryption scheme is robust or withstand any let's say cryptanalysis technique? No, we're gonna have a better way. Remember, we do have what we call shortcut. Now let's say, how can you utilize a shortcut in order to, instead you have the lifetime universe in order to decrypt this one, maybe you're gonna have a better way of shortcutting before this operation. So that's what we talk about. We cannot try 26 factorial, I think 2 to the power 88, I guess, if you remember that. Anyway, simple substitution keys, because it's gonna take forever. Can we be more clever? Take a look. That's the most important thing you need to know. When you start to decrypt the ciphertext, you need to collect some information. What the language they use? Yeah, they use English. Okay. They try to do what? Substitute one key with another key, or one letter with another letter, yeah? Okay. Can they use what is called guessing words? In other words, can you use what is called the word frequency, or can you use what is called, I mean, the letter frequency or not? As you know, in the English language, if you take a look here, you know that the frequent letter is going to be the E. Then the second most frequent letter is going to be T, and the third one is going to be A, and etc. Okay? So since I'm mapping, for example, assume that we have E, and you map E in the plaintext into this X in the ciphertext. Okay? And assume that we have T, let's say the plaintext M equal E, then let's say T. The ciphertext I produce, E is going to be, let's say, X, and T is going to be M. Okay? Assume that. So what I'm going to do here, I'm going to use what's called the frequency analysis. So that means here I need to count how many X do I have in the ciphertext. How many M do I have in the ciphertext? How many X, whatever, all the letters, okay? So you have the frequency of the letter. So you end up, you have something like this. For the X, you're going to have like, this is the highest one. This is X. Then after that, you're going to find the M is going to be the next one for the highest one. It's going to be similar to the T. So it looks like, you're going to say, it looks like, because I'm trying to guess, it looks like I said, okay, so this guy, since the X is going to be more the frequent letter here, it might be X. There is a high chance, high probability, that X is the encryption of the E. So I'm going to substitute X with E. Then M, it looks like, because this is the second high letter that I found in the ciphertext, so it looks like this ciphertext is say for T. So I'm going to substitute M with T, X with E, then see the plaintext, the ciphertext, how it looks like. You see that you start filling the gap there, and after that, this for the single letter. We can perform the same operation for the word, okay? I'm going to go over this one again here. But we, what you call the word frequencies, in the English language, you know that the first, or the most common word that has only one letter is what? Is an I or A. So if you found in the ciphertext that we have, let's say, I, let's say X something, Y, Z, M, Z, then after that we have I, and let's say something else, and or let's say D, and etc. So you say, okay, this is one letter. So it might be one letter, it might be I or A. Let's assume that's going to be I, or maybe assume that's going to be A. So you have two different versions. With plus the information that you collected here, you start filling the gaps. By the way, that's what we are going to do in the first activity. I'm going to go over this one later, more details. Okay, so we start filling the gaps. So one letter. So how about two letters? I'm talking about the word frequency, not the letter frequencies. You know what the two most words in the English language that you have contains two letters. Okay, so try to find out how can you perform M, for example, or double S, or double E, or double T, and etc. So you start filling the gaps. What is the three? I mean the most common words that contains three letters in the English language might be that. So if we found 3XYZ, so it looks like THE. Substitute this one in the plain text and the ciphertext and try to fill the gaps. Anyway, so it looks like we're gonna perform what? So how can we attack the message encrypted with the substitution cipher? We can use what's called as example the cryptogram puzzles. You know the cryptogram was the type of the puzzle that contains like a short piece, something like this. Yeah, exactly. Then a piece of encrypted text. Then you try to do it to analyze using the frequency analysis. So here either gonna be the word frequencies or the letter frequencies. Again, let's remind you with or summarize the word frequencies and the letter frequencies. This is the best way or approach in order to breaking the substitution cycle. You don't need to figure out and find out all the possible key because they permute the letter. So I have 26 factorial in this case. It's gonna take for a long time, but we do have another thing. Okay. So anyway, so I'm gonna use the frequency analysis for the word frequencies, or let's say the letter frequencies. Okay. So by word frequencies, we do what? What do you mean here exactly? When you are given a phrase where one of the word is one letter, so example here, and you have one word A, yeah? So the first, it's reasonable to assume that the corresponding letters is the popular one word like A or I. It might be A or I. So now we have two versions. You can say, take the plain ciphertext, take two copies. One I'm gonna substitute D, let's have different color, this is weird. Substitute this A, okay? And another one, I'm gonna substitute this one with I. And see what it looks like here. And here, by the way, if you found D here, all D must be substituted with A because you know that D is gonna have the same, transformation when you encrypt it, yeah? So if you have another D, this is just one example. Here it's gonna be A, and might be I, and continue. A, and might be I, yeah? And it looks like when you say and something, it looks like the value is I here. So I prefer I because it looks like if you have I now, it takes two letters or the word that contains two letters. If it's I, it might be S for the K. So now for every K, I'm gonna have S. So it looks like this is the right one. It's S. You see comma and S. You see your knowledge in language, you're starting breaking down the ciphertext. Okay, and continue doing this one. This one. This is for the word frequencies. For the letter frequencies, as I mentioned here, you need to know what's the most common letters in the language that you use in order to that you already encrypted here, or they have the ciphertext. We assume that English language, and you know that the most common letters in English is going to be language with what? E, T, and A, and O, and I, and N. Yeah, this is the most common. Let me see here. H. Yeah, we can check this one. Maybe. Actually, it's P. Because I know the decryption. It's P. But it's good. I'm going to show you, by the way, how to analyze this one. By the way, you are going to do this one in the first activity. Maybe I'm going to upload this one today after today's class. I do have another class, by the way. And by the way, they send me email, they change the way that, or the format and the software that you use in order to upload or post, the recording of the class to the Blackboard. They give you only 2 GB, which I almost consume them, but they give me another way in order to upload the recording. So starting from today, expect that you're going to have a long time in order to use their way in order to upload the recording. So by the end of the day, we do have let's say activity 1, which looks like something like this. Before we go to activity 1, let's take a look to have some information given corresponding to the ciphertext or the cryptogram that you try to decrypt. It's simple substitution. We use permute one letter by another. So this means A is going to be B, C is going to be X or whatever. So it's not mono alphabetic cyber. We assume that no letter is going to encrypt it as itself. So that means for this one, for example, if you have P, W, E, C, you know for sure this one is never going to be when, because E cannot be decrypted or encrypted by itself, as itself, I mean. So eliminate. So if we found V here, this one never be V. This never be O. So another piece of information. Okay? Then I ask you to analyze this message. So again, you have to use the same thing we talk about. The word frequencies and the letter frequencies. The word frequencies, that take a look for the check, for example, the given phrase, where one word is it might be a letter. I mean, if you have, for example, one letter long in the phrase, so maybe you can assume this one is going to be corresponding to the popular one, A or I, and similarly you can guess the common two letters, then the common three letters, add, etc. I will give you what the common one letter, the common two letters, the common three letters in English language. So it's going to help you. Then for the letter frequencies, the most common letters in English is going to be A, E, T, A, O, I, N, and the least common, by the way, is going to be the J, X, I think Q, Z. Correct me, guys, the native speaker, I guess. So if you look at, for example, at a given ciphertext, the most, and you need to do what is called the most encrypted letters. You need to count the occurrence with every single letter in the ciphertext if you want to use the letter frequencies. And based on this one, you need to just to compare this one, what you have with the letter frequencies that you have in the graph here. Here. This is the plaintext. You have to build another one for the ciphertext. Count how many A's, count how many B's, count how many C in the ciphertext, okay, until Z. Then try to compare. The highest one, or the most popular one letter in the ciphertext looks like this is E. The next one, it looks like T. The third one, popular one, it looks like A. Substitute this one in the ciphertext and see what's going to happen, okay, and keep going. So just begin, let me show you here. I'm going to give you this. Then after that, I want to go the class activity here, something like this. Okay, so I give you this is ciphertext. It looks like something like this. I give you the space, so you see that this one word, this is the second word, this is the third, this is the fourth, this is the sixth, and etc. Okay, then I want to ask you to perform this operation. You have to decrypt them. You are going to use what's called the cryptanalysis form. Which one thing? First, you need to find what the most frequent, English letter. So in other words, you need to perform what's called the letter frequencies. You need just to count the occurrence of every single letter here from A to Z in the ciphertext. How many A's, how many B's, how many D's. By the way, that's just activity, okay? I will give you like 1 point if you finish this one, okay? If you don't want to do this one, it's yours. So it depends on you, okay? So now then after that, try to fill the gap. I'm starting looking at to try to do what is called, the one letter English words, A and I. So now it looks like I mixed the letter frequencies and the word frequencies, okay? So by the way, the first time, or the first step here, once you decide which is the highest one, it's going to be E, T, then try to do what? Maybe have another copy from this one. And try maybe write over in the lowercase, for example, I expect this one going to be E, this one going to be T, this one Z, and etc. Or maybe you can start looking at this one and see, I guess maybe if you have 3 letters, it looks like that. For example, this one. Z, C, Z, Y, I guess it's going to be that because it starts at the beginning, the statement of sentence. So it looks like the C is T, the Z is H, and the Y is E. Oh, you have now 3 letters. You can use this one. Anyway, then I take a look at the first letter English, A and I. Now we'll talk about the word frequencies here. Just try to figure out, for example, the letters popular one single letter, or to say corresponding letter is the popular one word like A and I, substitute them. So you can put this one here, 1 letter words in ciphertext. You can find out what you found here. How many words you see, 1 letter O, what else? I think it's only O. You can add O, so O might be A, or maybe use as I. Most frequently double letters, double S, double T, double E, double L, and etc. And fill the 2-letter words in English, and etc. You try to fill the gaps here, and once you fill all the gaps here, you try to figure out and find out, what's the plain text. whether you're being able to have the plain text or not. Please don't copy this one and try to use the software. Try to do this one at least by hand. Okay? Okay, that's gonna bust it today. So anyway, so that's the first part with the substitution cipher. Okay. So generally speaking, frequency analysis, it works well with the substitution cipher, which is our shortcut in order to decrypt or decrack the system. I don't need to find all possible keys. Of course, for the shift cipher, the simple one is easy to do this one because you have 26 keys. But if you have the letters of this case, or the alphabet, so in this case, I cannot check all the possible keys. Then in this case, you can use the frequency analysis. And why the frequency analysis works in this case? Because we replace one letter with another. So we're still keeping the high frequency. For example, if you replace E with another letter, still E is going to be the highest, or the more frequent key letter is going to be appears on this ciphertext. So again, summarize what we try to do with in this case, and also the activity, class activity. Calculate the frequency table. Try to guess the most popular letters, then try to find the pairs of treble, the double, triple, and the pairs, trebles, and etc. And fill in the blanks and try to, and also plus your guess. If you take a look at the message, your ciphertext, you can tell it looks like A, it looks like Z, it looks like S, and etc. Especially if you have apostrophe, then S, so it looks like this is S. Any letter, I mean. The second way, or another way, in order to perform what's called the encryption of the classical or the historical encryption scheme, we call that the transposition. So in this case, I'm not going to substitute one letter with another. No, I'm gonna rearrange, I'm gonna scramble, I'm gonna mix the letter, rearrange the letter location of the message. For example, if you have as input, it's gonna give me A, B, C, maybe I'm gonna see the result of the ciphertext is going to be CBA, something like that. So I'm going to still have A, still have B, still have C, but the position of these letters is going to be changed, or it's going to be mixed, it's going to be scrambled, okay, or rearranged. So again, this one is going to do what? It's got the transposition ciphers. It's going to rearrange, the characters of the plain text in order to produce a ciphertext. So the key in order to perform the cipher in this case, you need to figure out or find out create a matrix. Okay, we have a number of tuples, a number of rows or columns or tuples. Okay, and you need to encipher the message by writing the plain text into the matrix by, let's say, rows. Then after that, reading the result of the ciphertext out of the matrix by column. So assume in this case in the ciphertext we're gonna use, for example, matrix 4 multiply 4. So I'm gonna write this attacker down. This is a plain text, and they use X here in order just to separate, let's say the words of the message. I'm gonna write this one, okay, by rows. Then after you write this one, so attack, add down. Then after that, in order to produce the ciphertext, you're gonna read the message or the matrix in the column wise. So A, C, T, W. Then after that, T, K, X, N, and etc. Okay? So in order to decipher this one, or decrypt this one, you can't take the message itself, and you have to reverse the operation. Okay? In order to try to produce the ciphertext that you're looking for here. So you can, for example, writing the ciphertext into the matrix by columns and read this one, the plain text out of the matrix by rows, because you need to reverse the operation. But the key here, I need to know the matrix. Matrix 3 multiply 3 by 3 or 4 by 4. If I don't know the right matrix, so I cannot produce the message. For example, if you said the matrix is going to be, I'm going to use the decryption, maybe 5 multiply 3, 5 rows and 3 columns. So in this case, in order to organize the data here, you are not going to be able in order to read the right message. Of course, for this case, if you have the the data, or you have the letter, you can tell it looks like attacker down part. Maybe you're going to retrieve or skip or leave this class as soon as possible, or stay away from the crazy person on the start. We do have another type of the transposition. We call this one the double transposition. So the double transposition, which is going to have the better way in order to perform the transposition ciphers. So in this case, we are going to what? To put the plain text into an array. The same thing, but I'm going to permute the rows and the columns in this case. Okay. For example, we could put the message, for example, that's given here, and say into 3 multiply 4. So you have 3 tuples and the 4 columns. That's the way that way. Then you have to write the message in the plain text. This one thing. Then I'm going to permute, yeah, the rows and the columns. So it's like more sophisticated than the simple transport cipher that we showed the previous slides. So here, suppose that we are gonna permute the columns with the 1, 2, the rows that we have 1, 2, 3. We have 3 rows, yeah. I'm gonna permute this one until, let's say, it depends on you, 3, 2, 1. So that means put the first, whatever you have in the first row, it's gonna be in the third row. The second is gonna be the same, and whatever you have in the third row is gonna be in the first row. So that's what we did. This first row is gonna be the third one, and this third one is gonna be in the first one. I permute, the rows. Then after that, you can permute, the columns. So the columns that we have 1, 2, 3, 4 columns. We have 1, 2, 3, 4, and I'm gonna permute them into what's called the following. The format. It depends what you try to do here. 4, 2, 1, 3. Depends on the choice. Yeah. So that means the first column, it's gonna be in the third. Let's say the fourth column is gonna be the first one. So that's what he did. The first column is to have a different color. It's gonna be the 1. Then after that, the second column is gonna be the same. And after that, the first column is gonna be the third one. So that one, we move this one to the third. And the third one is gonna be the fourth one. Okay? Then now you need to read the data and let's say you can say in the row. Yeah? Or if you can't do this one, the column, it depends on you. But you need to make sure that you have the same way that you perform the operation. Here we're gonna perform the example, we read the data in the row base. In order to decrypt them, you have to write down the data, let's say in the by row. Then you need to figure out how, have access to the key that we use here. What's the key? The permutation that we use in order to reorder the tuples or rows, and also the permutation that we use in order to order the columns here. So that's what you have. You have the plaintext here, and this is the CyberText, how it looks like here. Okay? In order to perform, decrypt this one, because right now if you give me the ciphertext and I know this is going to be written, or the encryption scheme, the substitution cipher, let's say the double transposition or the simple transposition, the transposition, not the substitution, then now we need to find a way in order to find the shortcut. Okay, can I find all possible keys? In this case, you have let's say the previous one, how many you have? 3 multiply 4. So you have to find all the possible combinations of the tuple and the rows. Of course, maybe this one is small, but if you have a larger matrix, you're going to use it to perform the operation, so you cannot tell. By the way, 3 multiply 4, you cannot tell. Maybe it's going to be a matrix 1 by 4, or maybe 2 multiply 6, or whatever, because they have multiple options. I don't know anything about the key. The only thing that I know, they use, let's say, transposition ciphers, and this is the ciphertext. Then good luck in order to estimate or in order to predict, the matrix dimensions used in order to encrypt the mask, and also the permutation for the rows and tuple. So it's gonna be maybe we're gonna spend a long time in order to figure out how can we perform that. But can you find the shortcut or not here? In order to find the shortcut, someone will say, can you use a frequency analysis in this case? It's not. Why? Why the frequency analysis is not working here in this case? Same number of features. Because what we did, you have A, it's gonna be what? Mapping to the A itself. The only thing that we did, we just reorder this one, but I didn't affect the occurrence, how many times A is gonna be appears. Exactly. We just counted the letters. We just rearranged the cursor of the letters there. I didn't change, for example, the occurrence, how many times A is gonna be appears. But the location, does our location going to affect how many times, for example, specific letter is going to be a call in the ciphertext? No, it's going to be the exact time that it appears in the plaintext. So if you try to create, let's say, this graph, you're going to have this is going to be the plaintext, and it's going to be the same one that you got in the ciphertext. So in this case, you cannot use the the frequency analysis in order to decrypt the message here in this case. Okay? But we do have ways how to perform that. Yeah. So one way to take a look, you need to reconstruct the matrix. Single transposition, guess the number of columns. This is the one guessing you can perform. Double transposition, that means you need to, for example, add the columns and the row. But we're still being able, you used to have one part, but I removed this one because it's gonna be time consuming, but we're still being able to try to figure out, crack the system, okay? I'm not sure whether they cover this one in the cryptography, class. I'm not sure because they didn't teach this course here, and I'm not sure about the outline, but we do have another class, cryptography, which cover more details, all the encryption schemes with how to encryption, decryption, how can we find out, or how can we shortcut in order to crack the system. Okay, what we learned so far. We can summarize what we learned into three different, terminology or ideas. Confusion, diffusion, and key secrecy, okay? Don't tell me it's confused because the class is confused here. Anyway, so what do you mean by confusion here? That's what we learn actually when you talk about the different cipher techniques, and we show you some, let's say, how can we attack them. So the confusion and diffusion are the two properties that of like basic operation that any secure system cipher must have. Okay? I know it's old, the Shannon, the cloud Shannon, the one that wrote the paper 1949, but still this is one of the main basics of the crypto security or information security. So let's take a look. What do you mean by the confusion first? The confusion is the technique used in order to ensure that the ciphertext gives you no clue about the plaintext. So by looking at the ciphertext, you have encryption scheme. You cannot find out and say, oh, it looks like since the ciphertext looks like something like this, then I expect that maybe this is the corresponding plain text, or it's easy for me to guess the plain text. Okay? How can you achieve that? Achieve this one using what is called substitution. For example, you're gonna find X, Y, Z, and etc., but you can't tell what's X, Y, Z. Of course, if you try to analyze this one, different story. But for the confusion, this is the goal here. By looking only to the ciphertext, I give you no clue about the plain text. Okay? So we do have a property that confusion is going to provide us, which is going to hide the relationship between the ciphertext and the key they use in order to achieve the ciphertext. That makes it difficult to find the key from the ciphertext. So if you take a look to the ciphertext and you see, oh, it looks like the key that you use in order to decrypt the message is blah, 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 blah. Okay? So again, based on the ciphertext, without the key, you cannot deduce or generate the plaintext. That's the achieve of the goal that we try to achieve here in this case. Okay? So, generally speaking, it's achieved, as I mentioned, by substitution techniques. Okay? So there is no leaks of information. You should not be able to find the pattern, so you cannot tell. That's just confusion. Of course, right now, maybe someone has said, oh, it's easy. I can take a look to what I have. Then I can, for example, figure out the goal here or what's the plaintext. Of course, but at least give you the idea that you have to achieve, then see how can we manage using the techniques that we have to reach that goal. This is the confusion. The diffusion is the idea that here, the idea of the confusion is to hide the relationship between the ciphertext and the plaintext. So what does that mean here? So that means if you change one character, that's the plan that we have. Someone has said, this is the plaintext and this is the ciphertext. That means if you change one character in the plaintext, this one is gonna should affect how many or how that should affect the ciphertext. So that's the goal we try to achieve. That little change in the plaintext is gonna produce, result a big change in the ciphertext. For example, if you change only one letter here, maybe you're going to see that many positions change in the plaintext, or the ciphertext, sorry. If you flip, we have one bit, a sequence of bits, zeros and 1. If you flip 1 to the 0 here, then you're going to see that you have many places in the ciphertext has been changed. So you cannot tell what's the relation between the plaintext and the ciphertext. Okay, that's the diffusion. The third, part or the third goal, third idea or the goal here, secrecy only based on the key, not based on the what you call the encryption and decryption schemes. Okay, and this one just show you a simple, funny, image is that maybe anyone, if you build your encryption decryption schemes based on secure algorithms, so in this case maybe someone can get this information easily. But if someone in this case tries to catch you or force you to tell them what the algorithm you use, you can say it's okay, Google is available, but I didn't know the key that you use there. Yeah. We're going to see later when we talk in the second part of today's lecture, when we try to cover the symmetric encryption schemes, we're going to touch these terminology again, the confusion, diffusion. Then we're going to see how can we build this block cipher or symmetric block cipher that based on these techniques. Okay. One thing I need just to back to the diffusion and forget to mention that to achieve this one, I'm going to do transposition. That's why we study substitution, transposition. Confusion by itself, or the diffusion by itself, in other words, substitution and transposition on their own are not enough. So you can, if you have built an encryption scheme and you only use substitution in order to try to achieve confusion, or transposition in order to achieve diffusion, you see that is not enough. It's not secure. It's easy for you in order to crack the system. Okay? So what if we combine the multiple substitution or multiple transpositions? For example, you see that we have, I will use S as substitution. I have substitution algorithms. I use this one. Then the result, this is input, for example, the message. Yeah. Then this is the key that you use, whatever, let's say shift by 3 or whatever. Then after that, there's one stage. Then I apply another substitution. It's like complex, is the key, another key, or the same key, whatever, and for the CyberText one in order to produce CyberText that we're looking for. So we have like multiple steps. I'm going to apply maybe, let's say 2 or more substitutions going to be applied. It looks like you have just only complex substitution. You think that maybe it's going to be a complex algorithm? No. With it's more secure? No, it's just going to be more complicated. The only thing you need to do, you're going to apply the same technique that you use in order to try to crack the system. The same thing if you said, okay, I'm going to build like a complex, you say, algorithm using based on the transposition cipher. This is the first one, then the output is going to be input to the other stage, etc. So we have multiple stages. Okay. In other words, you're going to perform transposition 3 times or 4 times or 5 times. The same thing. You still have the same problem. It's not secure. It's just you produce a complex transposition. So if we come up with an algorithm that mix both of them, so it looks like you have some, let's say, many stages. I'm going to do, for example, substitution. Then the result of substitution, I'm going to do transposition. Then the next stage, I'm going to repeat the same thing. More substitution, another transposition. In this case, we're going to have like the best of the both worlds, which I mean the base of the most of the block cipher techniques. We're going to try to build an algorithm, so secure algorithms. We're going to try to mix these techniques together. So it looks like confusion, diffusion, confusion, diffusions. Okay? One thing we need to add here, we talk about that before the monoalphabetic, cipher. Okay? So in this case, generally speaking, we're going to do what? We're going to encode or cipher or encrypt the plaintext, okay, using only one fixed alphabet. So if you have one alphabet, for example, A, and you have like a fixed mapping, A always, for example, my algorithm is going to be mapped to the D, and C also is going to be mapped to F, and etc. So every time, once you face A or find A in the plaintext, you're going to mapping to, let's say, exactly similar to the Caesar cipher. But Caesar cipher is only shift by 3. We need just to generalize this one, okay? Something like this. You can F, they say X, for example. A also they're going to be X. The goal here, just the most important thing that you are going to map only 1 to 1, and this is going to be fixed, okay? So every time find A, you're going to be mapping whatever letter you want. And it's going to be fixed here, okay? Regardless of the position of the A in the plaintext. The same thing that we did, let's say the symbol, shift, okay, or substitution. And you can't do this one, yeah, it depends on you. For the simplicity, you can say from A to Z, and you have 0 to 9, so you can come up with algorithm. From 0 to 9, you can tell 0 is going to be A, for example, 1 is going to be 2, 8 is going to be 0, B is going to be 9. So you can mix. For simplicity, we'll just say from A to Z. But you can expand this one to any character or to anything. Okay? So the possibility here, we might have many different monoalphabetic substitution ciphers. So right now, just to show you that you have a letter can be substituted by the letter. Yeah, but as the question is right now, we can do this one, expand this one, going to be any character, okay? Or any, let's say, even special characters. You can use a plus, minus, multiplication, division, whatever. You can expand that, okay, if you want. Okay. The problem with this one here, given, let's say, a few minutes, okay, and several people, or maybe you work in the computer, or as a group here, give you the ciphertext message, the secret content, okay, are revealed. It's easy to break down this system, okay? Why? Because it looks like if you figure out have, for example, a few letters, you manage to find the right, mapping or decryption, or they say the way that, or shift, if you, for example, shift by 3 or by 7, or maybe random permutations. You can do this one, permute the alphabet randomly. It's fine in this case. Anyway, if you have a limit number of attributes, maybe, or a character, I managed to have A correctly, it's going to be successfully mapped to the C, this correct this one, B, F, and etc. A few of them, it's easy for you in order to correct the system. So, can we make this one harder? Yes. One way in order to make this one harder, instead we have a fixed, let's say, substitution of one map. For every single letter is going to be mapped to the exact number regardless of the position of this, let's say, a character. We can use, let's say, more than one alphabet, okay, which switching them systematically. This type of cipher is called polyalphabetic ciphers. So it looks like in the, for example, letter A, it depends on the position of the letter A. If it's going to be the first letter, or the second, or the third, or the fourth. So it looks like you have, maybe it's going to be changed. Sometimes A is going to be mapping to the D, and sometimes it's going to be mapping to C or whatever. So give you an example here. You have a plain text, okay? Plain text, for example, okay? This is a plain text. You need to cipher this one. So you can't tell, let's say, okay, I'm going to use the key. It's going to have different alphabetic permutation. What does that mean? Maybe the first letter is going to be shifted by 3 to the right. The second letter is going to be shifted by 4, okay? And the third letter is going to be shifted by 7, something like this, okay? So 3, 7, or 4, 7. What I'm going to do here, I'm going to repeat this one. So the first letter L is going to be here shifted by 3, okay? I by 4, V by 7. And the key here depends on you. Maybe you're going to have 3 different, let's say, permutation, let's say, different alphabetic permutation. Maybe have 2, 3, 4, 5. It depends on you. Then I'm going to repeat this one. Since we still have a plain text, I'm going to repeat 3, 4, 7, 3, 4, 7. This is a great example here, by the way. Not big, of course, because it's Liverpool. Okay? So here you see L in this position, I'm going to shift it by 3. L here, when it was here, I'm going to shift it by 7. You see that it's not fixed. Every time you find L, it's going to shift it by 3 or by 7 or by whatever. No, it depends on the position of this letter here. What else? You have another letter, it's going to be, yeah, O here, great, another O. O in this position here is going to be shifted by 3, and here it's going to be shifted by 4. That's what you call polyalphabetic, ciphers here. So I'm not relying on a fixed placement structure, but we are going to use, different substitution for different level positions. So make it harder. Of course, it doesn't mean that it's hard. We're still being able to crack the system, but it's not easy compared to what is called the monoalphabetic cipher. Clear, guys? We're going to have an example how to use that. Beginner cipher, okay? This is a polyalphabetic cipher in which the number of different substitutions is also part of the key. Give me a second, I will see. Of course, remember, we're still talking about the classical encryption schemes or cryptography system. It's not the modern one. This is old. All of them is easy to crack them. Right now, you write your code and whatever, either it's going to be short or large, it's going to be easy. Of course, remember, if you have a small size of the message, it's easy to crack this one because, for example, as we give right now, what if the message contains only 3 characters, or maybe the size of the message similar to the number of permutation letters that we're going to use? Yeah, so the shorter, yeah. But you said letter frequency. In this case, yeah, we can use that. Give me a second. Let me finish the beginner here. Then after that, we're going to see how can we use the frequency analysis. It's going to work. But the most important thing in this case, you need to find the size of the key. Yeah, let's say we said the 375, 5. Yeah, this is the first, the second, the third. 375. So if you figure out the size of the key or the length of the key, you can see that the first, let's say the first letter and the fourth letter and etc. are encrypted using the same key. So I'm going to treat the first and the fourth as one part, as like a separate ciphertext. And the second letter, which encrypted by 7, and the fifth letters, I'm going to treat them separately as a separate, ciphertext. So you can apply the letter frequency and the word frequency in this case. But the key, in order to perform this one, you have to tell me exactly how could you estimate the size of the length of the key. But yes, we can do it. So Victory is going to is the polyalphabetic cipher, which is the same thing as you mentioned here. It depends on the number of different substitution you're going to use. And this is the key. You must hide the number of different substitutions and the length of the size of the key. This is very important. Okay? Exactly. This is, remember, you're right. This is the same thing. This is Virginia cipher. The German Enigma encryption machine used the same technique based on this one. And use this one because, let me go over this one. Actually, I'm not sure. I think I didn't teach cryptography class here in the IIT, but I guess if we teach, the one that teach one is supposed to go over different techniques. How can we crack this one? So we're going to see, for example, what they did exactly, the mathematician, how he cracked with his team the Enigma encryption machine. But actually they got, let me see, okay. I think there's a movie, I watched this one, it was interesting. Maybe you find the paper that explain exactly what they did. It's going to be interesting how to perform that. But the Enigma machine, the encryption machine is based on the Virginia cipher here. It's the polyalphabetic ciphers, and they use like different substitution as a part of the key here. And they change this one every, I think, day, every day, yeah. Change this one every day. So anyway, how can you perform this kind of techniques? Okay, how can we encrypt this one? Generally speaking here, or beginner, cipher use 26 multiply 26 tables, something like this. This is the way how to perform that. Okay, remember this is only from A to Z. I didn't add numbers and special characters, etc. This is a simple thing. Okay, so we do have 26 multiply 26 table. We have from A to Z. Okay, and we do have what is called a row header, this one, and we have, let's say, the column header. Good. And this table is usually referred as Virginia tableau or table or square, different names, okay? So the first row of this table has the first 26 character. Then the second row is going to do what here? Starting from the second, I'm shifting the letters to the left. One position in a cyclic way. So this means shift to the left, whatever is going to left over is going to be pushed to the end. So you see that I'm shifting this one to the left, B, and A is going to be added to the end. Then the next row, I'm going to shift this one to the left and push B at the end, etc. The last one looks like you have shift this one to the left, Z here, and this is add the Y at the end, and the beginning going to be the same one. Okay, this is how can we build this table. So how can you use this one in order to perform the encryption? Okay, so again, the key is secret. The size of the key and the letters and the way that, or you say the substitution is going to be secret here. Okay, so the first thing here, you have to pick a keyword. We call this one a keyword, okay, which is the encryption key that we're going to use here. Let me go up here, back. So assume that we have the message that you want to encrypt, and this is, I'm going to use the keyword is kind of contains 3 letters. Either going to VIG or write the letters, for example, 7 or 16. I don't know where the position of V in the alphabetic, I don't remember, but you can write, for example, 27, 24, 6, and 7, something like this. Or use the letters here, the same. Then you're gonna do what? Pick a keyword, VIG, the size is 3, which is my key secret. Then I'm going to write the keyword what? In the way that it's going to be across the top of the text that you wanted to encrypt. So this is the text, okay? And this is going to be the keyword. You see that? I'm repeating VIG, 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 and etc. Continue until it's going to be enter. I mean, match all the plain text. Okay? Then, now starting to perform encryption. So it looks like either, by the way, you can perform the same thing that we did with this substitution cipher. Message plus, let's say, M plus, let's say, K module 26. That's one way to perform that. Or maybe you can use the table itself. So how can you use the table? This simple way. To encrypt, I'm going to pick a letter in the plain text. For example, it's going to be T. And I have a key, it's going to be V. Okay? Let's go to the table here. Either way is fine, by the way, okay? I'm going to use these letters, okay, the keyword letter and the plain text letter as the row index and the column index in order to find, or help me in order to find the right encryption and decryption. Either we're going to use, for example, the keyword letter from the column or the, how do you say, column or the row. It's either fine, okay? So anyway, I'm going to use the index for the column, for the key, and the plain text letter I'm going to use as index to the row. And you have a V here. Let me write this one here. And the plain text is T. And you just to find the intersection here, which is going to be O. So V, this is the key, and this is the message. You say T, corresponding ciphertext is going to be O. Continue with the next one. The next one is I, and the letter, I guess, is going to be H. So I'm going to go with I here. And you have H. The intersection is going to give me a plain text, the ciphertext, sorry. It's going to be P. Edit it. Continue. In order to decrypt, you do have the key and you have the ciphertext. I'm going to use the same table, but in different way. Or you can use, the decryption algorithm that, or the notation that you use with the substitution cipher. 26 plus C minus K module 26. Okay, let's use the table here. I need to use a different color here just to make sure that you can use the different. Yeah. So in order to decrypt this one, you're going to use, one letter with the key, sorry, and one letter from the ciphertext. Okay, use it as index. I'm going to use the key of the letter from the keyword as an index here for the column, which in this case is going to be V. Okay, then that's different. I need to just reverse the operation. For the encryption, I use the letter keys for the plain text and the key in order as index here for the row and the column. Here's the opposite. I will use the letter from the keyword as the index for the column, and I'm gonna use what? So I'm gonna use what you call the letter heading of the column that contains the ciphertext letter is the needed plain text letter. So here I'm looking for the ciphertext that look at the header that if I use the V as key, or what is the header at the row in order to produce the plain text. So I know this O, this is the ciphertext. I reach ciphertext using this V as a key, so definitely this is gonna be the plain text here, which T. So it's like reverse order. Again, for the encryption, I use the letters for the keywords and the letter from the plain text as index for the column and the row. For the decryption, I will use the letter from the keyword as an index for the column, and I need to use heading of the column that contains the ciphertext letter in order to tell me exactly what's the plain text corresponding with this one. For here, you have I and H. I'm going to use I with the key for the column, and I know that this is B, this is the plain text, yeah? Sorry, the ciphertext. How can you reach this one? By using H as, or H was the plain text at that time. Did it confuse you? What's the ciphertext in this case? The key O, the message K, what's the ciphertext? Yeah, the key O, okay, I'm here. And the message is gonna be K, and it's gonna be Y. In order to reverse the operation, you reach Y by using the key O, so definitely this is the plain text. Or you can use different story here. You can perform, something different using this, okay? This is another idea. You have from A to Z, Yeah. Then after that, you have to repeat A to Z and count from 0 up to 25. You know that, like the mapping that, I mean, just to try to find a way in order to map it from A to Z. I'm going to use 0 up to 25. Then after that, H1 is going to be 26 up to 51. And you can use, for example, encryption V with the letter T. You know what the V is going to be 19, and the letter T is going to be, let's say, V is going to be 21, and the T is going to be 19. I have two different colors. Add them, then you're going to figure out, add up the numbers, going to show you which, letter you're going to use or produce as a ciphertext. Or you can add them and compute the model 26. Both of them is going to be the same thing. So different way in order to perform that. In order to correct this one, you have to know the period. What's the length of the key? You do have to access the table used. Yeah. If in order to help you, or maybe you can use a mathematical, or let's say mod 2 in order to try to compute the, let's say, whatever, the cipher or encryption, okay, or decryption is. Can you attack in the ciphers? Yes, which is your answer question to the just. So establish a period. You need to make sure that how can you find the key length? What is the first one? Sometimes I'm not gonna give you the data that organizes the same thing. I give it to you in the, let's say, in the class activity or the examples that we have. Maybe I give you the data like has, let's say, different period, fixed period, okay? For example, if you have Illinois Institute, something like this, I'm not going to give you like a ciphertext corresponding to, for example, maybe you have 7 letters, and then after that another block, another block. It's not one-to-one. I'll try to mix this one. So maybe I'm going to have like create or make sure the data is going to be resulted into 5-letter block. So divide the data, this 5-letter block, the next 5-letter block, the 5-letter blocks. So mixing the words that belongs to or more words is going to be in the same block, or maybe spread over many blocks. Make it harder for you. So if you take a look at this one, you are not going to gain anything. Okay, you cannot use the letter frequencies here, or to say the word frequencies, because the 5 letters, or this block that contains 5 letters, does mean that this is the actual word in the plain text is 5 letters. Maybe it's going to be, for example, I am instructor, something like this. When I encrypt this one, X, Y, Z, D, F, G, then after that, I'm going to produce the first block. I'm going to give you X, Y, Z, D, F, and the second block is going to be G, and etc. So you see that now you cannot use the word frequencies because it's not. I try to hide, the ciphertext or the plain text. So try to make it harder for you to know that to say, oh, it looks like this is 1 letter, this is encryption, 2 letters, and etc. Okay, but the text that they give you for the queries or ciphertext and the class activity is clear. You know that this is 1 letter, this is 2 letters, and etc. You can tell. Yeah. Okay, so that's all about the attacking ciphers. So what I need from you to know here, you know the definition. You know that, for example, how to use a visionary, for example, for the encryption, decryptions, substitute, let's say, shift or let's say Caesar cipher or shift cipher, symbol substitution cipher, how to perform encryption, decryption, and the same thing with the transposition. Okay, so we have a terminology we said that the crypto system is secure if the best known attack that we try to all possible keys. Okay, which in this case I'm talking about the brute force attack, or they say exhaustive search key or exhaustive search key search. Crypto system, generally speaking, is insecure if any shortcut attack is known. And remember, we cannot guarantee that or prove that there is no short attack for any encryption system or shortcut in order to attack any crypto system. So the question here, whether there is any completely secure ciphers exist? Actually, yes. Which is the one that we're gonna cover? Actually, we're gonna see one. Yeah, exactly. One-time pads. That's what we try to cover here, and I'm gonna tell you why it's secure. Yeah. So, as a vernon, another name to the one-time pad. That means, what does that mean, one-time pad? That means you're going to use the key only once, one time. For every single encryption, you're going to use this key to encrypt the message. If you try to encrypt another message, you have to use different key. And the problem here, the size of the key must equal to the size of the message. So that means if you try to encrypt 1 gigabyte file, so you have to come up with 1 gigabyte, let's say 1 gigabyte multiply 8 bits then this is the size of the key that you're going to use. Okay? Remember, the problem here, you need to find a way in order to perform encryption or send a message using this kind of encryption scheme. You need to find a way in order to distribute the key first. And people, said that, okay, argue that it does make sense. In order to use this encrypted message using one time key, I need to find a way in order to securely send that key, that's the size of the key similar to the size of the message, to the receiver in order to allow me to perform the communication. So people agree with that. If you manage to send the key securely, why then send the message in this case? Yeah? So there'll be waste of the time. If you and the problem here, repeating this one, if you try to send multiple messages, yeah, that means you have to manage to find a way how to securely send the key here. Okay? So anyway, so that means in this case, which sometimes you call this one information theoretically secure, that means based by looking only or knowing the ciphertext, you cannot get any exact useful information about the plaintext. Other than the length, yeah, you know the length of the, because you know it's 1-to-1. We have 1 gigabyte, so you know the length of the key is 1 gigabyte, or the length of the message is going to be 1 gigabyte. Okay. So let's have an example here. See how it looks like. How can we use this one, and to see whether we can be able to work this one or not. So again, we emphasize that it's secure if it's used correctly. What do you mean the correctly? Just emphasize that. The key as long as the message, the keys must be random, the key never reused. Okay? Let's see how can we do that. It's generally speaking, this kind of one-time bat is based on what is called the exclusive OR operation. Okay? So you know the exclusive OR, yeah? So we have X and Y, 0, 0, 1, 0, 1, 0, 1, 1. So result only going to be X exclusive or Y. That means it's going to be true only when exactly one of X and Y is true, or 1. False are both true or are both false. Okay? So that's the only way it's going to be equal true or 1. Okay. So we have just a few property about the exclusive OR. It's similar to exactly, it looks like you're doing the summation of modules 2 in this case. So it's going to produce 0 or 1. So exclusive OR, X with Y, is similar to X plus Y mod 2. Exactly. We have like associative and commutative, okay? 0 is the identity element. So if you have X, K, exclusive OR, whatever value with 0, it's similar to 0 exclusive OR K, which is going to produce the K here. Its own inverse, that specific for example, 1 exclusive 1 equals 0, 0 exclusive 0 equals 0. So the element with itself, exclusive OR is going to produce 0. We're going to use this one later. We're going to see how can we help us in order to encrypt, decrypt, and do some properties associated with the one-time back. So the way how to perform encryption, starting, I think we talked about this one last time, it's useful for every single encryption scheme you write to give me like the mathematical notation, how can you perform the encryption and decryption. Here, if you have a message, for example, whatever the message encrypt the message, let's say M, using the key, okay, so here using the one-time bat, I'm going to use M exclusive OR K. So it looks like you have M plus K mod 2. That's the operation you're going to perform here. And you perform this one in the bitwise. So that means you need to convert my string or whatever the character that you have into bits, yeah? And you do this one in bitwise. So that's why I'm going to use Ki and Mi Ki, which this means the corresponding value or the corresponding value to this bit that you wanted to use the information. So you can say Ci is equal Mi if, or let's say in the case Ki is equal 0. So if the Ki is equal 0, in this case here, it depends. It looks like we have Mi exclusive OR with 0. This one equals the value of Mi. If the Mi equals 0, the result is going to be 0. If the Mi or the current bit equal 1, the result is going to be 1, which satisfy the X exclusive OR, right? It's going to give me the right result. The Ci we said equal to not or negative or negation of Mi if the Ki is equal 1. So it looks like we have Mi exclusive OR with 1. is equal to what here in this case? It depends on the opposite value of mi. If mi is 0, the result must equal to 1. So this is equal not mi. Yeah. If the mi is the current bit for mi is 1, 1 exclusive over 1 must be equal 0, which in this case is the negative of mi. So those is holds. Okay. The decryption. In order to decrypt the message, let's say the encryption, we did this one as this encryption message. The decryption, I just use the same key and the exclusive OR with the same message. Sorry, for the ciphertext. So the encryption of, let's say, K of M equal M exclusive OR with C, let's say K. And the decryption uses the same key for the ciphertext. I'm going to say C exclusive OR with K. Okay? So let's have an example. Assume that this is the way, this is my ASCII code. Whatever the way that I represent the data in binary representation. Assume that the code that we use has only 3 bits. And those are the letters that we have, A, B, C, H, I, K, and P, and Y. Okay? And they give you like the plain text. You need to encrypt this one. In order to encrypt the plain text, that you need to do here. For every single, you convert from whatever the alphabetic representation into the binary representation, ASCII code, whatever. Okay, in our case, we convert this one to the following our system. Maybe have a unique, let's say, mapping system. So here for the H, we have 001. For the A, it's going to just convert 000 and etc. And assume the key, this is the key. Remember, the size of the key must equal to the size of the plain text. So the plain text here, 3 multiply 5. Then in this case, the plain text must be, or the ciphertext must be 3 multiply 5. Okay? In order to perform the encryption, remember I'm going to apply this formula. So we call this one bitwise encryption. That means bit by bit. 0 exclusive OR with 1 is going to be 1, 0 exclusive OR with 0, 0, 1 exclusive OR 1 equals 0, and etc. Then after that, you just are mapping this one to your system that you use. In this case, 100 in our case is going to be K, 111 is going to be Y, and etc. So this is the encryption, this is the plain text, sorry, this is the key, and this is the ciphertext. In order to decrypt, I'm going to perform what's called exclusive OR. Exclusive OR is not expensive operation, it's easy because I'm performing addition modules. So it's easy to implement this one, it's going to be fast. Okay? And K, I would say, sorry, the ciphertext. I'm going to write this one ciphertext, use the same mapping system that we have, convert to the what our system, the mapping system that we come up with. Then I'm going to use the exact key. Now I try to perform the bitwise, let's say, exclusive OR. So 1 with 1 would be 0, and 0 with 1 here is going to be 1, and with 0, 0, 1, which in this case is going to be happy. So we managed to encrypt and decrypt. So far, so good. But we still keep in mind, the size of the key must equal to the size of the message in order to allow us in order to perform the encryption and decryption. Okay. This is generalized, that's formally definition for the one-time bad or kernel. Assume that the message and the ciphertext and the key space, all of them in the binary representation. So the size, we put this one, the size, all of them are going to have the same size, the same length. Okay? Which, yeah, we agree with this one. The second one, this is the encryption function, or this is the decryption function. And the reason why they are working here, if you take a look here, you have this is ciphertext, and when you decrypt the ciphertext, this we're supposed to have or produce the same plain text. So we substitute in order this formula. The notation, mathematical notation used in order to encrypt the message, which in this case K exclusive OR with M. Then after that, I'm gonna exclusive OR with the K. This is the C, right? I just substitute, the value for the encryption method. Here, K exclusive OR K, you know that self-inverse, so it's going to be 0, exclusive OR with the M, this produce, the same message M. So we managed to use the exact key, we managed in order to decrypt, to encrypt the message. So far, so good, hopefully. It works fine. The security based on the length of the key, the key itself, yeah, because if you know this key, if you use this key, let's continue. No, Mac, yeah, this is the new one, the new update, the security updates. And the guy, I know it's only 2 days ago they just launched this new update, but you have to do this one. They start since morning, it took longer, although it's 3 gigabytes, but it took longer. I think everyone download the same update. Now they said, now starting to start the computer. I said no. Then they start showing me many messages. I ignore it. So hopefully still being able to continue the class. Okay, so this is important in the encryption scheme. We're going to see that we're going to use in today's lecture. We'll start looking about the let's say symmetric encryption scheme. We're going to see that we're going to use in order to perform what's called the SIM cipher. So just seeing what is SIM cipher. Just speaking, we have like the message, okay, and the message is going to be as a strings, or let's say a sequence of bits, zeros and ones. Okay, I'm going to perform okay, the message MI. I perform exclusive OR with the key. This will produce the CI. 0, 1, 0, whatever, and 1, 0, 1, 1, 1, letter-wise or bit-wise, I'll produce the CI. In order to perform the decryption, I'm going to use the CI. I'm going to have to use the same key I, or the set of the key that I have, in order to produce the MI, which is going to be 0, 1, 0. That's what we call the SIM cipher. It's a very important one. We're going to see this one. How can we implement this one using this technique? Okay? Of course, we're going to see later. It does make sense. I'm going to use the same size of the key, similar to the same size of the message. But we have a trick. We're going to use this one. We're going to use the key in order to use or create what is called pseudo-random bit string, which allow me to generate, the required or number of bits that are required in order to encrypt any message. That later we're going to talk about this one. But for a reason, when you study what the one-time bad, it's going to help us in order to implement the SIM cipher later. Anyway. The problem with this one, you know that it works if the message of any length, that's good, but the problem, in order to encrypt or decrypt, you have to use the key, and the size of the key is similar to the size of the main message. So you do have a problem. How can we securely distribute the key? Okay? So why the key cannot be reused? This is a similar situation. We don't listen. We send, for example, the create C1 equal encrypt K for the M1, or the message M. Then the message 1, for example. Then after that, I'm going to C2, I'm going to use the same key, in order to encrypt the message 2, and send both of them here. Use the same key. So I'm going to see what happened. The bad guy was Alice and Bob. You send C1 and C2, right? So the Oscar, or someone in the intercept the communication, going to have C1 and C2. I do have both of them. What I can do in this case, the simple thing, I know that you are going to use, specific algorithm encryption. You know how to compute the encryption and decryption. I know that for the C1 is going to be like M1 exclusive OR K, yeah, and the C2 is going to M2 computed by M2 exclusive OR K. What if I do my exclusive OR with C1 with C2 here? If you do that, I'm going to eliminate the key or get rid of the key. So it looks like you're computing that M1 exclusive or M2. Yeah, that's the problem. One problem here. So we see what kind of information you can get in this case. Yeah, if as an attacker I know M1 and M2 is going to be resulted 0, I know the guy is sending the same message. That's one thing. If there are blocks of the data, I can't tell that those blocks of the data have the exact value of the same information. This one is going to be added up, yeah, with the rest. That's one thing. So if whatever the value, remember we talk about to say K exclusive or K is going to be 0. If they have the same value, they're going to be, this means the exact value is going to be reduced 0. Okay, this is going to help us somehow, because remember, I'm trying just to deduce any piece of information that might help me in order to get the message. Yeah, I'll try to crack the system or find even, a pattern. What do you have here with your system here? And you know that if the bad guy managed to have, for example, C1 and get somehow, remember that maybe he managed to get access to the or compromise pop computer. So in this case, you can get C1 and you're going to get M1, the message corresponding to the C1. So by exclusive OR C1, exclusive OR M1 is going to produce what here? The key they used. If you use the same key again, so I'm being able to decrypt whatever the communication that I have here. The further communication. That's why don't use the same key twice. Okay? And again, the most important thing here, why we don't use this one mostly in the practice, because they say, why you don't distribute the message instead of the key that we use in order to encrypt the message? Because remember, 1 gigabyte, for example, for the message, you want to encrypt it, you have security send 1 gigabyte key securely first. If you manage to do this one, so why are you wasting your time? Send the message securely, and every time you want to send the message securely, do the same way that you use in order to exchange the key. Okay? So we talk about, in this first part of today's lecture, about the basic types of ciphers. We said that substitution ciphers and the transposition ciphers. The advantages, disadvantages, and give you some examples. Different encryption schemes, all of them are based. Yeah? We take a look to different ways of how to, let's say, attack or crack the system. We manage in order to, by knowing the ciphertext, how can we get, the plaintext, or maybe get the key. We do have a different ways. We call this one cryptanalysis. We don't have two different ways either. We're gonna brute force attack that we try to find every possible, or try every single key, yeah, based on the key space. Or maybe again, you maybe use statistical analysis or maybe frequency analysis in order to try to access or try to retrieve the information that you're looking for. So if you want to learn more in this part, there's also, the reading, if you want. Okay, we have 2 different textbooks. Each of them is going to have different chapters if you want to learn about the classical part. Thanks, guys. That's all for today. See you next week.